Welcome everyone. My name is Maciej Ramotowski and this is XDC 2021 workshops. The first topic will be coordinating the CI effort for Linux plus user space, led by Martin Perez. Martin, the stage is yours.
Hello everyone. Let me start with my screen share. Actually, no, let's the first thing is that some people here do not have their names set. I think it would be way easier for everyone if you could set a name that would enable more so we can reference who said what. Then once this is done, I'm wondering if you would like to introduce yourselves. So far, it looks like most people already know each other. I don't know about the philo-jitzers. Okay, maybe let's not do that. Let's go straight to the workshop discussion. So I have prepared some slides that can be used as support for the discussion, but everything is gonna be a discussion. So it's not like first I present and then we talk. So it's just a way for us to have a direction and make sure also that we don't get stuck in one topic only. So I'll be sharing my screen. And here we go. Can anyone confirm that this is shared?
Yep, we can see.
Yep.
Very good. So the agenda is pretty simple. Since I did not get too much feedback about what was more interesting for people, I kept it to 1 hour for trace-based testing and 1 hour for kernel testing in GitLab. I'm assuming that the latter is not going to be as demanding. So if we have some time left over, we could go back to trace-based testing. Any concerns with the agenda or something you would like me to add? I'll take that as a no. Can I ask Charlie to take notes about the discussions? Charlie Turner.
Yeah, no problem.
Sounds amazing. Okay, so I came up with 4 categories for trace-based testing. So the first one is, okay, so creating the traces, how it can be painful and slow, and it's a little bit of an art. Then confidential trace execution in a CI infra is another topic that is, well, important. Then the next one, reviewing frame outputs. So this is from a human point of view, like, is the frame what it's supposed to be? And that's another art form of its own. And the last one is, how can we teach a machine to do that? So this is pretty much research oriented at the end. But let's start with the easiest part, which is let's make traces. So there are multiple tools that allow you to make traces. So the original one was API trace. So, well, it's good for OpenGL, OpenGL ES, DirectX 8 to 11, and there is DirectX 12 being added right now. Then there's graphics reconstruct, which is Vulkan oriented only. Then we have renderdoc, which is not the same type of traces as API trace of graphics reconstruct. It's more like for a single frame, but it supports OpenGL and OpenGL ES, DirectX 11 to 12, and Vulkan. And we have its maintainer in the call today. Then, so creating a trace can be difficult, especially in Steam, because there's multiple layers of and directions. So Steam is the one launching the game and things like this. So that can be a little tricky. I'm sure there are, like, we could work towards making this easier. And then it can be super slow. So it can be as slow as getting frames per second, or in the most pathological case I had was more like a frame per minute or per 30 seconds, really. And yeah, it makes reproducing issues extremely difficult. Then selecting the relevant frames is the next thing. Let's say you have a trace that is about a minute of gameplay. You don't want to be looking at, let's say, 60 frames per second times a minute. So that's quite a bit. You don't want to compare that many frames. So you want to select which ones are the most important ones. So how do you do this? Well, you need to find what frames are the most representative of scene, whatever could work. So as an example, I'm gonna show the Tomb Raider, Rise of the Tomb Raider benchmark, and how it can, what can be used there. So first thing is you want to make sure that the menu is rendering correctly, because if your game is working but you can't get there, that's bad. So that's the first one. Then on so for the people who have not seen the benchmark before, then it's going to be a bit difficult to know what is going on, but I hope that it's going to be still understandable. So I chose this particular frame because we could see the protagonist from up close and having some mountain in the back, some snow, and that was the only frame of the benchmark where you could see her face clearly. So that's somewhat important in this. I mean, it's not super important in the game, but it's important that the protagonist's face is there. Oops, sorry. Then the next one is a bit more interesting because you get the metallic effect on the climbing gear, the radio, lens flare. You can see some motion blur on the snow, and again, you can see the mountains and the fur also on the jacket. Then you've got a new scene where you can see Lara in a different outfit. So that's another thing, because you don't want to check only in one place, because potentially, well, one outfit is going to be utterly broken and you wouldn't see. So as many outfits as you can try to collect. And you can see some God rays here. Then some reflections in screen space, lens flare, things like this, and new items here with the ice picks. Oops, sorry about this. And here, that's again another scene with a flowing river, which we had not seen water before. There is rain. Here you can see traces of rain drops and a waterfall here. So it's pretty useful. Very good. I'm going to leave a pause here if anyone has some concerns or something they want to say about creating the traces before we move on to trimming. Okay. Then trimming, that's the first thing that everyone will agree is problematic. So first of all, why do we want to trim? We want to trim traces because they are super big, so in size, but also because you want to reduce execution time. I mean, why render frames that you're not going to be dumping? There's no point. So the problem is that removing empty frames can be very hard, because frames can depend on previous frames to render. And so there's been work done by Collabora recently to improve the OpenGL trimming. Then for Vulkan and Graphics Reconstruct, it's supposed to be designed for trimming, but then it's not been working super reliably for me. Hopefully this is something that can be improved. And for DirectX, I've never tried. So did anyone try to do this? Crickets. Well, I think that's fair. So is anyone working on trimming or something related? I mean, we had Daniel Stone. Maybe he could talk to us about OpenGL trimming here?
I can.
Go ahead.
It's good enough for the traces that we already have, and it should work for most Steam games. But of course, we can find corner cases that because so we could make it practical because the generic case can take big servers days. We had to come up with some heuristics, and maybe we need to add a few more. So I don't know, just try it out if you want to add traces.
Okay, but this is really so far you only focused on OpenGL, right?
Yeah, that's correct.
Okay. And who was that?
Tomeu.
Okay, of course. Very good. Well, I guess for Vulkan, we'll need to see with LunarG if they are willing to spend some time on this. And for DirectX, I guess we'll see with API Trace how things are working. Okay, then next topic, infrastructure. So why do I say that we need to do like confidential traces? Well, the problem is that non-free games, which is the majority of the games in Steam, by majority, I really mean it. The problem is that they contain non-redistributable art, like textures or videos or things like this, and traces are capturing that. So we don't have the rights to redistribute, so we should not redistribute it. So the problem is that they can be quite big, the traces. So over a gig is about average. And so if we have, let's say, 100 traces that we want to run, and they are all 1 gig, then it's going to take a while to download all your traces. So let's say over an hour, especially if you have multiple machines downloading from the same server. So what you want to do is cache these on the test machines, so as you don't re-download it every time you start a job. The problem is that the machines can be used for multiple jobs, so we need the cache to be encrypted, or at least make sure that only the jobs that are allowed to access these traces need to be allowed. And yeah, that's it. So the way things are done right now with FreeDesktop and Mesa CI is that the traces that are run are only the public ones, if I'm right.
No. We are already using non-redistributable traces for FreeDRAIN only, and it works basically as you described. And there's a series of people who have access via GitLab to the repository, Minayo repository that contains them, and that includes Marsh, the bot. So basically, the idea is that for FreeDRAIN jobs, when they get in a pre-merge testing, they can be tested with those traces, but the job is allowed to fail because who knows, maybe a contributor doesn't have access, isn't in that list, and we don't want to block that code from being merged if that person cannot debug it. But those people who have access could, in theory, get them and debug them. The only problem is that so far no bug has been found by that job. But it's only 5 or 6 traces. So the infrastructure is there. We need to come up with more traces and put them to use.
Okay, and how do you store them locally and make sure that the other jobs don't have access to them?
Locally, so there's a repo which is not a public. It's in the graphics CI namespace in GitLab.
I think he meant on the actual DET. The answer is we don't. So for most of, well, yeah, at least for our Lava stuff, we don't trust the eMMC to burn out in, like, yeah, we'd just kill it in a week if we actually wrote all of the full content into the storage, so everything's pulled off NFS. That includes the traces where we've got an Nginx caching proxy. So that will cache all of the content, but it will only serve it if you've got a valid auth header. Like it goes and does a head request, I think, to MinIO to check that the request is authorized, and then if it is, and it has been seen by the Nginx that we run in both the Collabora and in the Freedrino labs, then it serves it out of its local cache. So, like, it's not as fast as being on the device, but it's at least Ethernet fast rather than internet fast.
Yeah. So in the case of the Valve infra, so what I've been working on, we have so far about 60 traces, like real traces, DirectX traces of real games, where we get, I think out of these 60 traces, we have 220 frames that we extract. So one trace can actually generate more than one frame. And as I was saying, the traces are big, so they're more than 1 gig. And one issue that we had with using NFS or something like this to download the trace as we need, then the issue is that potentially if you've got a network issue, it's going to influence your the execution, and that would make it difficult to know if something is failing, why it was failing. So as much as possible, we are trying to preload everything and then start the job. And when starting the job, the machine is basically freewheeling, and we only get the serial logs to know what is going on. And if it is stuck, then we can reboot the machines or things like this.
I wonder if the answer then, rather than trying to do encryption where you then have to burn a ton of time decrypting it, is since you've already got things isolated via B2C, perhaps it could be about running a something like Nginx or whatever that can do request validation in parallel on the local machine there, serving from local storage, which the CI container wouldn't have access to, only when it's mediated.
Actually, go ahead. Oh, okay. So so we found a solution already for this, and we are actually using the X4 encryption. It's called FS-Crypt. So it's not just for X4, but it is there. So basically, we can tell the kernel, hey, for this folder, you're gonna use this encryption key, and then it's gonna encrypt both the content and the file names and metadata. And the only thing we need to do when we need to access this, well, it's actually a Podman volume that we encrypt. The only thing you need to do when accessing this volume is you need to tell the kernel what is the key. And so basically, we just need to send the key via the kernel command line. And this is stored in GitLab as a masked variable, so you don't see it in the logs, and it decrypts things locally, and there's virtually no performance cost for this.
Yeah, so we have tried to steer away from static keys like that, partly because, if you need to sort of add a new scope or extend the scope or whatever, then it gets kind of painful. But also because it is easier to leak that key out into the log, and then you not only have the content that's been leaked, but you have a pretty persistent way to get at that content when you leak the key, and unless you've got some elaborate like rotation and distribution system. So yeah, again, that's something I wonder where maybe where we're better served having those keys stored more local to the content and then given out on demand when you supply an appropriately signed JWT, because we've been using that for the private traces repo just so we can do a little bit more fine-grained decision on who should get them. Like at the moment, the rule, if I remember right, obviously people with access can access that MinIO storage in jobs from their repositories, but then also I think the rule for Mesa is that we allow merge requests against Mesa to pull them if the job has been triggered by Marge. So it does let us make slightly more smart and sort of fine-grained decisions there.
Yeah. So for us, indeed, the only access control that we do is when we want to mirror the cache, when we want to update the cache to the, well, let's say like all the latest traces. So in boot to container, which for the people who are not aware is a project that we started, which is an initram FS that is the minimum that you need to run containers. So it just acquires an IP, formats the local drive to cache everything, and so we can ask it to create. It's like a declarative way of saying what you want to have. So you say, hey, I want a volume, and I want to mirror this particular MinIO. I want it mirrored, like download the updates or pull on, and then there's a list of conditions, and then I want to push things back to MinIO, and again with a certain list of conditions. And so this is when the access control is done. And rather than using JWT, we have been so we have something a bit like Lava that so we call it the executor, which is basically doing time sharing between the machines. And this one is creating credentials that are tied to the lifetime of the job. And these credentials get additional privileges sometimes if the client calling already has access to the traces and provides credentials. Then some of the if these credentials that were provided are belonging to a certain group, then we can add this group to the dot access right. So this is.
But sorry, when you say credentials that are scoped to the lifetime of the job, I mean you already get that from the JWT, right? Like it's signed by GitLab and it has the job namespace and project, the user, the time-based scope as well in that.
But the problem is the time was 15 minutes, right? So you can just stop it at any point. Whereas what we've done is really like at the second the machine is off, then the the credentials are lost. Like so it's a bit more fine-grained time-wise. But
Yeah,
then what you
that makes sense. I mean, there is the job ID, and you could query just to go check on the job status, and if it's stopped, then obviously reject it. So all of this makes sense, to be fair. I'm just seeing if there's a way that we can share more stuff between us rather than building
absolutely. So
separate bits of info.
So what you were describing, the JWT, for me, this was something that would be the credentials that you provide to the executor to prove that you have access to something. That would be a JWT credential. So that would be, again, something that can be leaked and it would be rolled.
Yeah, it's per job and the payload signed. So even if you leak it, it's only good for the lifetime of the job. The valid only until field is by default taken from the job timeout plus when it started, obviously. But yeah, you could do an additional step where you pull out the job ID and you go query the job status, and you don't allow it if the job isn't actually running anymore.
Yeah.
Martin, if I may, I think the main difference that you are having with what we are doing on the overall GitLab infra and what you're doing at Valve is that you are willing to have a local cache for every trace for every runner. While what Daniel just described is that you can actually rely on the entire infra to have access and to have the fine-grained access to the various logs by using a separate machine that has a cache that would be just an Nginx proxy that would do the validation for you. So I still believe that what Daniel described is much easier to put in place because you don't need to have any identity provider or all this kind of stuff on top of that, because the job already has the JWT token from GitLab, just needs to validate with the infra, and then you get all you have. And given that Nginx is local to your machine, well, unless you're having 100 machines in a 1 gigabit network, which I hope you're not, it's not very, it shouldn't hurt that much to have that instead of having local storage cache.
I definitely agree that if you can get away with not having a local drive and not needing to cache things locally, then this is way easier when you can have a trusted and untrusted boundary that would be separated by the network. Unfortunately for us, I believe that the traces that we have are way too big to download them and keep them in memory, for instance. I mean, let's say that we have some traces that are 7 gigs. And if you have 16 gigs of RAM, then, I mean, you're going to run out at some point. And they are a bit more demanding than, GLMark or something like this. So...
Yes, but you have, with B2C, you have the ability to have a local disk cache.
Yeah.
And you can actually just trash it after each job.
Yeah, absolutely. But then you would need to download, let's say, the 64, or right now we have about 65 gigs of traces for 60 traces. And so, I mean, I think it's been taking about, when one machine at a time was downloading it, it was about 20 to 30 minutes to download. And then, of course, if you've got multiple jobs in parallel, then that's going to be multiplying the time. So
yeah, just upgrade the switches. Use 10 gigabit network.
10 gigabit for everyone.
Yeah, it makes sense, and like I do think there is a kind of a halfway house. But yeah, I guess it'd just be nice to see, even though there's the 2 use cases, right? Like one is we want to do upstream testing in Mesa of traces that people can see the output of, but aren't allowed to have the actual traces themselves because we're not able to redistribute those freely. And then the other case is doing completely internal secret testing on traces no one can even know about. So those are kind of different, and yeah, I guess you're working at a different scale, but it would be nice to see if there's a way that we can reuse at least like 90% of the same infrastructure for both. Like, even if you do end up distributing the store locally and you need to pull an encryption key, like if the authentication mechanism to get that encryption key was the same for both non-redistributable and remote Nginx pulling of traces versus secret and also local encrypted storage of the traces, I think that'd be really nice rather than just building up 2 parallel worlds.
Absolutely.
For what it was, I'm pretty sure, Daniel, you know already about that, but I've been checking on migrating my new packet into the new cluster. And while doing that, I can't use the exact same infrastructure. One of the components that I need to add is KeyClock, which is an identity provider. And I wonder if we could not use that opportunity to also provide some sort of private keys that way at the GitLab infrastructure, so that you could really use directly within your job. Like instead of just saying, okay, let's put your private key in the CI variables, you would use the JWT token to identify yourself with KeyClock, and then KeyClock would allow you to give you back whatever key you want using a vault or using something else. Maybe that's something we can work on.
Yeah, I think this was the recommended way by GitLab to store secrets, because the masked variables, that I think it was as help text around it, like, hey, if this is really something sensitive, don't put it there, put it in, I think it was KeyClock indeed.
It's well, usually they suggest to use Vault.
Oh, Vault, okay.
But KeyClock is just the identity provider. It's not the. It's just a tool that allows you to say, okay, I'm the job from GitLab. Can I get something else out of it? And then you this something else, this other JWT token to identify with any other component, being Vault or being anything else.
Mm-hmm. So the infrastructure that we are doing is something like Lava, where you would have the GitLab runner just basically queuing a job in Lava. And so if you have 10 machines, you have 10 GitLab runners, and each of them is tied to one machine. This way you can easily stop pulling jobs from GitLab by just pausing the runner, but the machines are still available for running other things. What we are trying to achieve is actually to have the same machines being available from GitLab or GitHub and potentially other instances of GitLab. So we're going to have a lot of different runners on the gateway, but then they're going to all map to the same machines. So that's going to be an interesting problem. But
yeah, that's another part of the reason we're not building a whole ton of stuff like local storage into our Lava Lab, because that's shared with kernel CI as well.
Mm-hmm. Yeah, exactly. And so this is the reason why we have let's say like a very maintainable interface basically at the client level, the client of the executor. And what we have been, when designing the interface for the client, we've been thinking about how it would be used by GitLab, and we don't want to be, making it hard. So basically, it's just a couple of secrets that need to be shared, and how these secrets come to be, this is something that can be done purely on the GitLab side. And so we have not been leaking abstraction interface, abstraction. What's the word? We don't have a leaky abstraction, basically. As much as possible, we're making it airtight. So we have a local min.io that is just used for sharing things in the infra, and this is not shared at all with FreeStop. And then if we want to send file to the machines, you download from wherever and you upload it to the local min.io, and this is done by the client directly. You just provide a folder saying, hey, share these files with the test machine, and this folder is going to be put on in min.io, and then the changes that are done by the test machine are going to be downloaded back at the end of the job. So the interface is really just files and STD in, STD out.
Yeah, conceptually that's pretty similar. And yeah, I guess coming back to Auth, like the main jump that something like KeyClock would give you as the vector for releasing secrets is that it does let you be a little more sort of fine-grained and discrete in how you do things, rather than just every job in this repo can access this token at all times, and that will let you decrypt stuff. So yeah, it's similar to like Vault or any other programmable like identity and secrets engine. Yeah, either way, I think the main thing is probably just to make sure that those secrets, as much as possible,
Or
like
rotated.
are rotated and appropriately scoped, but also B, like putting them in the kernel command line is fine as long as you're not printing that command line straight back out, right? And then the other thing is making sure you use them through files rather than command line arguments or whatever, because even though GitLab CI will mask the variables for you, if you have a really unfortunately timed kernel message printed out, or your UART drops one character out of the secret, then it's no longer masked because it's not recognizable as the secret.
Absolutely.
Hypothetically, definitely hasn't happened to us in real life.
Yep. Sounds about right. But yeah, that's the issue that I would have with B2C currently, is indeed you put stuff in the kernel command line and this is leaked through, or like basically every container has access to it. And I've been thinking how to get rid of that. And well, I guess we could add an interface for boot to container to download secrets in files, and then we would mount them in the different containers. So that could be an interface, something that would be nice to have. I'll put it as a to-do.
What we do there with Lava is we stick a bunch of per job environments, including the JWT, into this pretty tiny rootfs overlay, and the first thing that the job actually does is to pull the overlay.
Yeah, I'm doing exactly the same with when I use boot to container with QEMU. Basically, I'm just dumping all of the environment variable into a file, adding the file to the disk cache, and then whenever you start the container within boot to container, when you just the command line for the container, you just say, okay, this environment file is the one you need to use, and whenever you boot your container, you've got all of your variables already available, which means that you don't need to pass the variable along.
Yeah, it's much. Go ahead.
No, go ahead.
I was going to say that we've definitely not been bitten by the fact that the kernel command line is limited to 2K. And when you have as many environment variable as, let's say, Mesa CI, then it doesn't fit.
Yeah, but using that file, I mean, if you just so for QEMU, it's easy because I can open the vdisk beforehand. But it should be doable to have some kind of, I don't know, stored somewhere variable file that you would pull whenever you run your CI. You put that in the cache disk, and whenever you start the containers, then you just pull that file.
Mm-hmm. Yeah, we have integration with Min.io now, so you can download shit from Min.io. It's fine. So that could be tied to your access privileges, and I could create two buckets, one for the job file, and one for the job secrets. And then I could have, as part of the interface, that AMP file needs to be named in a certain way, and then it would be downloaded and put as an AMP file to every job that we every container execution.
I would recommend not to enforce a specific file, but just let users to choose.
Okay.
They want to use.
Yeah. Okay.
That's just my opinion.
Yeah, but in this case, what you can do is just put the file in the volume. Yeah, you can already do it actually. If as I was saying, like in the client, you can say share this this directory, so you could have the environment file in the volume, and the volume is pulled before doing the container execution. So then you can just use --m file and then a volume. I don't know if we can actually use a volume slash, or if we need. You can.
Yeah.
Look at that, Podman. You're a good boy. then perfect.
I mean, that's what I'm doing on QEMU. I have the dash volume. You can put whatever you want. It's just a regular file system, so Podman have visibility to it.
Yeah, I was afraid that they would force the end file to be on the local file system, as either a relative or an absolute path, and so you would need to get the mount point of the volume. But then, if you can use a volume name, then this is fine.
Well, you need to have the mount point. Well, that's something we can figure it out later, I guess. But
yeah, and that's also something that we can easily patch.
Yeah,
I've been in the process of making boot to container. At first I tried to reuse Docker or Podman, but they were too big, and then I started making my own, and then I realized that actually there was a way to get Podman to be small. So I'm a bit more confident in hacking into Go now. Not good at it, but at least I'm crazy enough to do it. So yeah, and I guess this is something that would be upstreamable, which is what matters. Okay, do we have something else on the topic? Because maybe we need to move forward.
Yeah, if you can you open at some point a GitLab issue on FreeDesktop, on the FreeDesktop project, with what we need, and so the people there can also chime in and publicly discuss about that. So in the end, we got some requirement on what's needed on the infrastructure, because even if you're running jobs, it would be perfectly fine for you to ping keycloak if we have to install it on the infrastructure to use the same infrastructure to get there. So we need requirements, basically.
Yeah, that sounds good. I'll let Charlie take note of that.
Thanks, Charlie.
Okay, so next thing, reviewing frame outputs. So that's going to be a game. This is all about, as humans, we just want to look at frames and say, is it looking good or not? Because in the end, this is what you need to do when you get the execution, the results from the execution you need to know. So, are we ready? Is this frame looking good? So we can see here some decal flying, which appear to be from a gun, which makes sense. I mean, it is an old game. It's zoonotic. Reflections look fine. Yeah. Okay.
The color is a bit off.
No, the color is also fine.
Yes. Oh.
But then you could see like, oh, is this meant here? Who knows? Then, well, actually turns out that the head of this guy was missing. So this is the type of stuff where you realize only when having frames to compare. So here what you can see is a diff with every pixel that is different is fully red. And now on this frame, you can see how it's supposed to look. So here the head is not missing, and here the head is missing. Oopsie. Okay, next, is this looking good? Okay, well, here the shadows look fine. You can see the shadow through the the leaves there, looking good. Well, this is looking a little odd though. So, okay, and here is a bit more triangle-y than it probably would be in real life, but maybe the game is like this. Well, actually, that is the expected rendering. The previous one was Windows rendering this game, and this is the trace replaying on RADV. So congrats to the RADV developers. So indeed, this is gone. Here we don't have these very angly artifacts. Let me go back. And if you look at the dog, it's also looking not as crazy. But okay, well, is it really that bad? Like, would it be breaking the game? Well, trust me, when it's behaving like this, yes. It is really annoying to have this flickering. Yep. So, too bad. It's not very playable. Luckily, this is a Windows driver issue, not RADV. But I wanted to check if it worked on RADV, so that's why I made the trace. Okay, then what about this? Like, what the bloody is going on? It could be some misrendering of vertices, right? And because I don't see a default character, the main character here. And then what's also going on with these things around there? Like, looks like a dithering pattern, but looks odd. Well, let's see it in context. Oh, okay, so what the heck? Basically, what happens here is that when the camera is being obstructed by objects, the objects starts getting this dithering effect, and then the frame that was selected was basically covering completely the character. So if you don't have the video showing how it's supposed to be looking like, then you lose a lot of context. So that's something else that to take into account when reviewing frames. It's difficult to know, and I don't know you guys, but I don't know every game in the planet. So possibly we would need to start thinking about recording the screen around where the frame is taken and have that compressed. So for instance, this video is 1 meg. So it's basically doubling the amount of storage per frame, but that could be acceptable because it makes review more possible. And then I don't know if it's possible to also have not keep these videos for as long, or we would just store them somewhere else and not as GitLab artifact. Any thoughts on this? An additional benefit. Yeah, go ahead.
I'm not sure if that was super clear to all the participants, but you might want to increase your local frame rate in the Jitsi settings, because I think it's like 5 frames per second.
Okay, so I'll select still frames then.
All right.
So here you can see the dithering pattern applied when the camera gets close to the object, and this is why here you don't see it, but then you see it here when it's closer. And then for the explosion that we were looking at, basically it's when the character is jumping on an animal, then there is this cartoonish explosion. And so it was not the character being exploded in a bad way, it was actually meant. Thanks, Charlie. So anyone has thoughts about potentially storing small videos like this of the frame in context?
I'm not sure I understand the reason if we have a some reference frame which we know that rendered correctly.
Well, that's a good point. Indeed, you could say that hey, when you upload your frames, you upload a reference frame, and then in the description of the reference frame, you say, this is rendered as expected. So it did not look wrong to the person who made it. And indeed, if it looks close to this, then that would be acceptable. Absolutely. But one reason why you might want to use a short video like this is that you could start using it to detect if there are some how like temporarily the coherent the output is, so you don't have problems like, oh yeah, but here you maybe not see it. I don't know if you can see the light flickering in the curtains.
No, but I believe.
Yeah, it's okay. You have one frame here, and then I'll move to another one, then another one. Basically, almost every frame is different. So here, for instance, you see a lot of light there, and then a bit before you see the light has moved. So that's a bug, and we could do this sort of analysis, but then, yeah.
So the idea is to store a small video and a handful of frames in a trace itself. So we render not a single frame, but like 3 in a row, and then we are able to compare temporal stability.
Yeah, something like this.
Yes, makes sense.
I apologize for the dumb question, but I'm kind of lost in what you want to achieve here. Because as far as I understand, you plot the trace. If you have the expected trace, basically you just need to do the pixel difference between the two, right? So when need the video to be pulled? Somebody? Why?
So that's, yeah, sure. The video could be useful to bring context for the person reviewing. If indeed there are very few differences between the different GPUs, then you're good. You can just have a reference frame and see how close it is. We're going to have a section on doing the frame comparison. But yeah, I mean, there are some possibilities. It's just that from basically, like, what are you testing is the question. If there were not, I mean, if the rendering was off, but then it was consistently off, then like, would I have cared? Maybe not. So selecting frames is good, but then you're gonna just be looking at this particular frame. If at this particular frame the output was fine, then you will never know. Whereas this would bring a bit more context, and potentially you could have way longer playthroughs and find more issues than just what you would have found in a couple of traces. But yeah, you're right that the context was missing, definitely.
But so as far as I understand, I mean, that's what I understood. Those CI traces are used in the CI. So they are used by a computer.
Yeah, so okay, maybe let's go to the automated frame reviewing then.
Well, not necessarily, but it's mostly that I understand that there is a need to put some video in the context. But besides the fact that this is a nice practice to have, and this would help developer to understand that there is a difference, I just need to know if it's what exactly you want to achieve there. And if the question is, do we have the space to upload those or not?
That's the main question indeed. Like, can we, and do we just keep it for as a like basically from the reference frames? We would also have the reference video so we can somewhat look, but then we don't generate for every single run the output video, which would make sense. The reason why I put the video was just in the basically in the context of the talk. You needed to see how things were looking, and then that just led me to think, okay, maybe there is actually some value in having that. But knowing what we need and what we don't is basically where we are now. It's research. We need to know what we need and if this is going to catch things or not, all the problems that we want to catch and all this. So maybe let's just go to the automated frame reviewing, and which is way more actionable right now, at least. Okay, I'll take that as a yes.
Like that at a maybe.
Okay, so for automated frame reviewing, we have some challenges. One of them is that the frames are not necessarily, well, let's say you have a single trace, you run it on multiple GPUs, you're going to have different outputs. And that would come from, let's say, if the driver is the same, it's just the hardware being slightly different in the way it's going to run the different shaders. And like even temperature can have an effect on the output frames because of floating point precision. The order of operation in the floating point is I mean, if you do like A times B times C or A times C times B, you're going to get a different result potentially. And so depending on these operations can happen between shader executions using, for instance, what's the word? Atomic operations, or simply because you write back the result in a buffer somewhere. And so this is going to have some effect on either the vertices or the fragments. So basically the actual pixel color or of inside geometry, or just the edges, basically. And so let's have a look at some of the issues. So here we can see a diff between two GPUs for the same frame. So what is interesting here is that the purple color means that the pixel is different. So the vast majority of the pixels are actually the same, but then we can see these banding going on there, and then a dithering pattern on it. The dithering pattern can be different depending on the hardware, and it might also be done in a shader if they want to do that there. And then usually you can see around some of the geometry, there's going to be a lot of different pixels. Well, that makes sense because if actually for the geometry, this one is a bit better. So here you can see shit, right? So let's say this big blob here or here. The reason why it is like this is because this is animated geometry, that's grass. So very slight differences in the position of the grass is animated using vertex shading or geometry shaders or tessellation or whatever you want to use. And so slight differences in the vertices position that is calculated by these shaders is going to affect where the edges are. And when the edge moves, then you can have enormous differences. Let's say you had an edge that was black on a white background, then you could have literally go from black to white. So you can't just say that throughout the image a couple of if you can have a +1 or -1 on every component of every pixel, and that would be acceptable. This wouldn't work for something like this. I'm going super fast here because it's almost time to start with the kernel. So do you have any questions here or additional insights?
So I have a question, if nobody. How do you do today with those traces? Because those traces are used in CI, in Mesa. How is it working?
Sorry. So for the Mesa ones, all we do for those is we check the checksum of the produced image against a YAML expectations file. If that varies, then we throw an error. There's no there's no allowance for like small margins because we just can't really reason about that. For the comparison, we have all of the gold images in a particular MinIO bucket, indexed by checksum, and then whenever a trace fails, we upload as an artifact from the job the failure result, and then so Piglet produces HTML for the entire trace run, and when you click through that, we embed some JavaScript that takes the two images, compares, desaturates, and then overlays the error region, so you can kind of see them side by side as well as what's actually changed.
Actually, if I might add something, so the idea is not as much as if the person can figure out if the image looks good, but rather if any change in rendering was intentional or not. It gives an opportunity for the person committing that code to figure out if there's any change in rendering that wasn't known. Then, well, if a person can look at the diff and figure out if yes, that's what I intended to do, then the checksum gets updated, and that's it.
Yeah, you are absolutely right. And I guess this is a slide that I forgot to write. I was hacking on them until right before this discussion. So let's go through first the list of ways we could do this, and then we can talk about how to integrate this with pre-merge and things like this. So the comparing to known good frames and just using checksums is working great for post-merge, and we can have humans review the new frames. And it's okay for pre-merge as long as the output of your frame is going to be constant. But if you have any variance, which is pretty much like any immediate mode renderers that I've seen, then it doesn't work for pre-merge, because let's say that you would, let's say you have 3 different outputs possible for a frame on a particular GPU. In pre-merge, you're gonna see that, okay, the frame has changed and the new checksum is gonna be this. And let's say you review the frame like we were trying to do before and say, okay, it looks good or nothing too bad looking. Then you say, okay, well, I add the new checksum, and then you land the code. But then at the next run, you're gonna have another checksum. Then, oopsie, everything breaks down.
Yeah, well, if the results aren't stable, then one cannot use that. It's a flakiness. Why would we have 3 possible outputs for the same image if it's not because of arrays or undefined behavior?
So that was what I wanted to show here. So when you have more complex geometry, for instance, and the especially when you have something that is a recurring process, for instance, well, the grass, I assume that the position at time t is taking the position at time t-1 as an input, so the errors compound. And potentially, if you have collisions between the blade graphs, then there's going to be some, well, a bit of chaos, really. You know, tiny little changes that compound and make a huge error later on. And you can't, I mean, you can't go around this. The execution of each shader on every core is not guaranteed to be the same at every single run. So you cannot assume that it's going to be always like this. For some simpler GPUs, it might be a valid assumption, but at least for Intel and AMD GPUs, this is an invalid assumption.
But
if we're working with the traces and the collisions, so the collisions are made in general in the engine and the CPU, right? So if we are working with the traces, there shouldn't be any issues with these things.
If you're using the CPU, yeah, but I don't believe that they're using the CPU for everything. At least physics.
So you mean in the traces there are things computing collisions and stuff like this?
Yeah, that could be.
Okay, I didn't know.
So it's likely something to do with order of the execution of each,
yeah.
shader instance.
Yes.
Like we could process one vertices in one run and other in another run.
Yeah, and that could be due to, let's say, I was saying that thermals was there and that I didn't finish the list. Guess why? So let's say that if you're, it's a little hotter in this particular day that you run the trace, potentially you're gonna throttle down the cores, which means that your bottlenecks are gonna change. Your memory bandwidth is suddenly gonna be a bit more, a bit higher. So you're gonna be stalled for less time, and potentially your context switching is not gonna happen at the, like for the waves. And so there's so many things that can affect this. And basically, if a shader invocation depends on the output of another shader invocation, then potentially everything will go to shit. And well, the reality is that for complex games, there's a lot of this. And then, well, the output is becoming a bit more unstable. It still looks good. I mean, this looks fine. But then you're not going to have pixel accuracy, and GPUs have never been marketed as being pixel accurate. Heck, if you land an optimization pass, you're going to change the output because of, as I was saying, like A times B times C is not the same as A times C times B. It's close enough, but it's not necessarily the same. Is that does it make sense?
Yeah, I guess it doesn't make sense to do trace-based testing with those traces.
That's a very good point. I wanted to give you a per trace analysis of how much variance we get on all the different GPUs. I ran out of time, but I have the data, so I should have it during the conference, so I can come back with it. What I can say right now is that so wait a second, someone is not muted. Okay. So what I can say is that there's a 20% chance right now that a new frame being generated is going to be known, is going to be a new one. Yes, that was it. 20% chance that it would be a new one. So one every 5 or 6 is going to be a new unique frame that we've seen. And that's on about 6,000 frame outputs that we have for 220 different frames in a trace that are expected outputs. So if every GPU had the same amounts, then we would have 220 deduplicated frames, but actually we have something like 2,000 of them. So there's 10%. Well, never mind. Anyway, there's a lot of variance. It's not up for debate. There's very few GPUs that render the same output. That's all I can say. And
okay.
Yeah.
So yeah, in light of this, do we really? So I see variance modeling with where the image changes is something you mentioned later. So is this complexity really required if we had just, I don't know, an epsilon of pixel changes that were allowed on the whole image? would it be enough, or do we really need like locality information, like this part can change and this other part cannot change?
Yeah, I think you need locality, because if you go to that example of the grass where just the geometry's changed, like that's a pretty giant delta. And if you added enough for that, then you could be missing the grass entirely, or missing complete trees or something. So I think we definitely need something more rich to describe it. I just don't know what that is. Because yeah, a lot of what we end up seeing is stuff like either missing geometry or broken blending or something like that, where it can be relatively small but still pretty high impact.
Amen to that. I mean, if you remember the original issues there, like the missing head, it's like most pixels were fine. But as soon as you've got geometry having issues, as soon as you've got geometry having issues, then you can't expect that a small delta would be acceptable. Because as I was saying, if you've got a black edge, or let's say a black triangle on a white background, then potentially you are going to have a slight change in one vertex position, and suddenly your sample is not going to be on the triangle anymore, it's going to be on the background. And how much of a delta is that? Well, 100%. So if you could encode which pixels, like basically around every edges, you're allowing a lot more changes than you are in, for instance, the sky there, then that would make a lot of sense.
But do you agree that if you have a floating error sample, floating error in your vertex, and suddenly your vertex gets moved by 1 pixel, what matters is the locality of the pixel? So I was half joking in the chat. Can you just remove the bulk of those error by just downsampling the image, compare it with the downsampled image? That should basically give an average of each pixel. So you know that, okay, there is a tiny offset there, but it's acceptable. And then you can also compare the full image for the things that are actually different.
Yeah, in a way, it's what you're describing sounds like a 2D convolution, verifying basically that the geometry is matching pretty well between the frames. That sounds like a possibility. I'm sure that it would get a very, like a value, but the problem with these convolutions is that there's no unit, so you don't really know, like, well, you could say, like, what is the optimal using auto convolution, but then I don't know. In any case, I think we can agree that this is all research, and what we are building right now is a database of frames that is manually tagged as being acceptable or not. And once we have this data, then we can start making algorithms or try different algorithms and see which ones are working. I mean, everything we're going to do is heuristics, and if people want to try their hand at this, then we would have a data set, and I think this is the best we can do. What do you guys think?
I think that's where also the context of the trace comes into play, because with such instabilities, interframe instability becomes more important. Like if this grass would jump around between frames too much.
Exactly,
like,
that's something that would, and we would not be able to catch it just by looking at one frame.
Yes.
Well, you read my mind. I mean, there is also truth in what Tomio was saying, like, pick better traces, bitch. I'm sorry. But I mean, but this is also something important. You don't pick like, you know, areas without grass because you want to know if the grass is working. Or you want to also check that your water is working. So it's like, it's real life. It's annoying.
Yeah, I think it makes sense, but I also think it's possible to do this incrementally, like start with the simple stuff, and as we add more traces that have this weird grass stuff, we can improve our system.
Absolutely. This is amen to that. And I would propose that whenever new trace we add, we basically use it only for post-merge, build a model of the variance, and then if we see that, you know, like once basically the trace proves itself in this particular GPU, that, you know, it's reliable enough, then we can use it for pre-merge. But we'll need to have these two stages. And if a particular trace is tricky for pre-merge, then what do? Well, we just improve our variance modeling or find other ways of detecting this and blah, blah. And in the meantime, the trace is not affecting pre-merge.
Yeah, I think, I mean, even before post-merge, if you just want to find pure environmental variables, then, you know, just queue those traces up to run like 100 times a day against the same build of Mesa and the same kernel, right? And see what falls out of there, because when you go to post-merge, you're introducing not only environmental variants, but like, you know, small near optimization variants or whatever.
That is true, but then this is also something that humans wouldn't necessarily care about, the output, the slight output difference, and so we don't want to be focusing too much on stuff that don't matter. And
So I agree, but I think it would be helpful to just have it isolated. So yeah, the, you know, temperature, load, whatever variance you were mentioning, like if you could model that first and separately, then that gives you a pretty good understanding of, you know, these are the bits that do just change, and it's not because we've optimized things slightly differently, it's just that they'll never be the same.
Yeah. The difficulty is that the machines need to be used also. So I don't know. So what we've been thinking about is creating an enrollment process. So whenever there's a new trace, we want to see where it's runnable, because not every GPU can run every trace if there are some features that are missing, for instance. And as part of this enrollment process, we could try to run the trace like 10 times on always the same Mesa version. And that could be giving us at least a good idea about, well, if it is not somewhat stable, then it would be 1 out of 10 times or 1 out of 100 times that where it would be problematic. But yeah,
but that will still not address the issue when you land a compiler optimization or something. But yeah, it would be a good start for random GPU stuff, hardware stuff.
In the end, I think what would be the goal of this automated frame reviewing is to have a reference frame including where we are accepting some changes, and this would work for every GPU. And then this way we can just add a new GPU and then have the reference frame already there. So that means that adding machines to CI, when you add a machine to CI, you don't need to suddenly review 200 different frames, different traces. So that's potentially 500 frames and compare them to all the other outputs, because that's unfeasible. So we need to think from a human perspective, are they looking close enough? And yeah, so that's going to be an important thing. This needs research. Okay, but I think we will have to go now to trace-based kernel testing. I think we are at 20 minutes over time. Okay, so unfortunately, I ran out of time for kernel testing, so I just have a couple of opens. Does anyone have any other open than these? Okay, so let's see if something comes up. So I have a question for Daniel Stone and Benjamin Tissoir. Can everyone now use GitLab for their kernel tree? Because a couple of months ago, that was not recommended, and I'm wondering now if this is okay.
I wouldn't say everyone just please clone this particular repo and go for it, but we can definitely see people using it one by one. We are already starting the nouveau guys to use GitLab and submit merge request. I think AMD is already using that too.
Yeah, absolutely. Yeah.
So it's fine. As long as suddenly there is not an announce on one of the LKML that say just please use GitLab for everything. And suddenly everybody starts doing that.
Yeah. Fridrino's there as well. I think those smaller trees are completely fine. The ones that worry me are obviously DRM tip, DRM MISC, and also DRM Intel, since that has about a bajillion CI pulls per day. But yeah, for the smaller ones, I think it's fine. Like, we seem to be scaling pretty well. Hopefully the storage is in pretty good shape now. So as long as we don't DOS it from day one, but we can just ease in a little bit, I don't see the issue really.
Well, that is good news. Okay, well that settles it, I guess. And then we can prove first that things are working for smaller drivers, and then grow towards DRM tip. But I agree that this is going to take a while.
Are there any resources somewhere about how this workflow should look like with GitLab used with kernel tree? What is the process for submitting patches for review? Whether we have hybrid mode for developers to work with mailing lists, or we use mailing lists only and there is just some data pulled into GitLab? How does it work in practice, and what is the plan to convince developers to switch?
I don't think there's any good answer to hybrid mode, because all of them fall into an uncanny valley. Like, you're for sending out from GitLab to mailing lists and people, everyone's going to immediately complain that it's HTML mail, and then for people sending back in from mail to GitLab, people are going to complain that it's not in the right place in the UI and it's disjoint and breaking threads and all of this. That was one of the things for Mesa originally, is that everyone really wanted a hybrid mode, but no one could really figure out how to make it work. As far as how the workflow actually happens, yeah, there's definitely nothing mandated, and we don't really have a particular best practice we can point to either. But that's exactly what the Nouveau people have been doing, is trying to try out a few different models of workflow, and how that would integrate with things like, handling pull requests and pulling patches in from the list and getting them up there. That's all the stuff that they're trying to figure out at the moment, like how would this actually work in practice. So I would probably look at what they're doing and go speak to them and ping them as well.
I think ultimately we don't need to migrate the workflow at all at first. We can just switch from git.freedesktop.org to gitlab.freedesktop.org and just change the git URLs and not change anything else. And this should already give us some CI post-merge at least.
For what it was, I know that at Plumbers next week, I think, one of our fellow colleagues is gonna give a presentation of how we switch to GitLab for the Rail kernel. We did not use the same kind of like incremental process. We switched directly from using a mailing list to GitLab over a couple of months. But I think the main thing is that there is no, as everybody is saying, there is no right way of doing it. It's much more depending on the maintainers, how they want to handle things, and if people are getting comfortable enough in merging stuff. So yeah, the Nouveau approach is good because they are testing things, and as long as everybody is okay with that, up to Linus in terms of does Linus accept a merge request from Dave that has been through Penskeggs and that have some non-maintainers, non-official maintainers applying merge request. I think we are fine there. We can do things incrementally.
But my concern with this is, let's say that someone is sending a pull request or trying to change an internal interface of the kernel and has to send patches to pretty much every subsystem, then it's also unreasonable to ask these people to create an account in every single GitLab instance or GitHub instance that would be the canonical one for the project they are actually merging into. So I think we'll have to have some sort of hybrid way, but maybe what could be done is that the maintainer takes the patches from the mailing list and then makes a merge request directly and have CI run there and then merge using the merge button. So I don't know what you guys think about this.
Yeah, I mean, that's effectively already what happens today, right? Like, you know, massive list discussion happens, and then at some arbitrary point, the maintainer goes through and applies and merges, and yeah, I don't really see a way around that.
Yeah, so there's always going to be a hybrid mode. That was my point, but I guess the core contributors to a project can be expected to make merge requests on the project directly and not just send patches to the mailing list.
I mean, there's definitely some overlap between like things like display and sound, for example, or I don't know, GPU and memory management. Do we really expect the sound and memory management maintainers to come to GitLab every once in a while to check if they have some reviews to make?
That is a very good point. Reviews. Well, there is okay, actually I have an answer for this. In GitLab, you can subscribe to notifications for any new merge request. And so just like you would subscribe to a mailing list, you would just subscribe to this. And so then you get in your email, in your emails, you can see what is going on there, but then you might not want to have updates on every, I don't know. I guess it's up to you. GitLab is pretty good for this. You can choose what you want.
Yeah, but I mean, it's not just like making sure that, for example, Dave and Linus are happy about it. It's also a bit wider than that. You have to make sure that the sound and memory management are happy about just signing in into GitLab and making sure that they'll get notified.
True.
Yeah, I think whenever you have a cross subsystem merge request, you can't use GitLab for that. Mostly because the maintainers, they don't have access. They don't necessarily have access to our GitLab instance. They could create an account, but we don't require people to create accounts unless there is a kernel.org, gitlab.kernel.org, where everybody is going there. I don't think we can expect people to send cross-subsystem merge requests. They would have to.
Yeah, I think the.org is taking kind of a separate direction. I think Constantin is actually working on having some kind of bot or something to send mails from pull requests. He said he was working on something like that, so maybe that could be like the bridge that we are missing somehow, but I don't know.
It's actually funny because everybody in every company is doing the same thing. They are all writing on a bot to actually make a bridge between merge request and mailing list. We have a bidirectional bridge. It's a nightmare to maintain for what it's worth.
But with GitLab, I think we could create an account that basically is using the original mailing list as and then every time there would be a merge request, then basically the emails would be sent there.
Yeah, the problem is that as soon as you have.
Oh, go ahead.
Sorry, I just want to emphasize what we currently have on our bot. It's a bidirectional bot. Basically, whenever you open a merge request, it creates a patch series on the mailing list, and whenever you submit a patch series over the mailing list, it creates a merge request. But then, when the bot creates the merge request, the bot has to also send the merge request to the mailing list. And so you need to have a database to ensure that what you are doing is correct and that you're with who sends what. So it gets messy really, really easy. And yeah, it's not easy. And I would suggest that we can actually trust developers to do things properly. Like if you're just touching your subsystem, you can definitely send out a merge request. But as soon as you need to touch another subsystem, you have to go through the regular ways.
I also don't think that the problem is creating accounts because other maintainers maybe just don't want to. And then they say, no, send emails.
Yeah, basically we have to adapt to the other maintainers.
Okay. Well, that's a very good discussion there, and I'm sure that indeed, like everyone has been working on bridges. For instance, myself, I have been making a bridge so as every time there would be a merge request, like patches sent to a mailing list, it would create merge request, not a merge request, just a pipeline in GitLab for testing. So it just does that. So use GitLab for just testing, and you keep on using the mailing list for submitting your patches and doing everything there. So that's the least commitment to GitLab, and we just use GitLab for running tests. And the bridge is bidirectional in the way that once GitLab is done executing the pipeline, it reports back. So I wrote the code. I need to finish merging it. I just need more testing, basically. And this is something that at least the patchwork maintainers were willing to lend. The reason why I made changes to patchwork is because I wanted to make sure we never drop a patch series, and because if there are some network issues, you can easily drop some emails. So that could be problematic. But let's maybe move on to where do we store the GitLab CI YAML, because like, do we want it in tree? I think Michel Denser was an advocate for this. Is he here?
I think this was discussed with Daniel Vetter a while back, and he said just drop them inside the drivers, DRM, something like this.
Okay.
Yeah, I was actually part of the discussion because I was playing around with that for Nouveau, and maintaining it out of tree is quite annoying and problematic because you don't get the nice GitLab integration, because in the other repository you will want to change your pipeline, but you can't verify it actually works. It's basically a nightmare to maintain because I had to, adjust the Nouveau project and point it to my custom CI file to check if it actually still works or not. So in-tree is really the only option here.
So is it possible to tell GitLab to look for the YAML file inside the subdirectory or something? Or do we really need .gitlab.ci.yaml at the root?
It can be
That's
anywhere.
possible.
It can be in a subdirectory or a different repository as well.
Okay, so should work fine.
You can even have a different name. you can use foo.yaml, it works.
True
No one
that.
will ever know.
Okay, so now the next question is going to be, like, what do we want to test? I'm sorry, the dog is crazy. Because, I mean, let's say that we would like to test. Oh, okay. What should we test, as in which mailing lists or which projects? And then what do we run for each project?
I think what the Nouveau tree, what Carol has been working on, was at least basic compiling, basic check patch, ensuring that I don't think you introduced spores, but these are the 2-3 things that you basically need. Having a boot run would be nice. I think we can do that through QEMU, at least to ensure that the kernel somehow boots if there are changes outside of the DRM code. Then it's entirely up to the various people managing the CI, their own farms, if they agree to see more testing.
I mean, once you get into boot testing, that's sort of exactly what kernel CI is for. I think the main problem with kernel CI though is responsiveness. It's always been very much a, you push your tree to Git, and at some point in the next 24 hours, you probably get a bunch of results, but not necessarily. So I think in terms of pre-merge, that would be the hardest thing to cross, because no one's farms are really set up for providing real-time responsiveness with kernel CI, which is, to be fair, the only reason we can do Mesa CI is because we really aggressively prioritize it over kernel CI, and kernel CI basically just runs when idle. So yeah, I think that's the main thing, is that the results come back really on a best effort basis from all the farms that are there.
Yeah, when we were working at Intel, I was making sure that the latency of the results would be bound. And whenever it would get out of bound for whatever reason, then yeah, developers would freak out and not be happy about it. And yeah, that is very important. The real-time requirements. Mm-hmm.
Yeah, then like everyone's just used to almost zero reliability as well in terms of or availability, I suppose. So quite often you'll see results just go missing for a month for a particular class of device, and they're like, oh yeah, my lab went down, so I just turned it off, and then you don't notice unless you're specifically looking for it. So yeah, I think until we can work with the kernel CI people to have something that could work better for us, or figure out a workflow where, rather than doing it in line with GitLab CI, we'd sort of kick off a whole host of requests to kernel CI and just have something automated that collates it, say, 4 hours later or whatever. Yeah, I mean, I don't think it makes sense to build out all of our own hardware farms and duplicate all that effort, but until we find a way to bridge that gap, then we're just stuck with QEMU, really.
Well, that's an interesting take. I I would not have. I'm not sure trusting someone else to maintain the machines for a project is a good idea, especially since, you know, let's say for Nouveau, there's going to be new GPUs that you want to add, or things like this, and having access to the farm is pretty crucial. And my experience with having, let's say, contractors or outside technicians that are not really into your project deal with the machines, it's a disaster. There's just no way around it. It never worked, and even when automating pretty much everything you can, if they don't have a vested interest in the project, or if they don't have, actually, there's literally in the farm that we have, and that is maintained by some external contractors, I have on the screen a list of self-checks, and if the machine was not, a couple of days ago, they did some changes at our request, and the machine was not on, and they did not even realize. And that's going to be the reality whenever you have other people maintain a farm basically for you. They won't know, and I don't believe that kernel CI would be helping us here, because, well, this it's just, yeah, it's machines, but machines, like, what configuration is it really good for your system? When are the machines going to be available? You need all of this to be at your it needs to be in control, and I don't believe that the machines in kernel CI are ever going to be somewhat in your control.
But then who's going to do it?
Aha! Well, I have a talk about how to make it cheap on Friday. I still need to start writing. But yeah, basically make it cheap, because everyone, pretty much every kernel developer has enough machines to start a CI system. But how do you make it easy to maintain? That's the question. And so I'm gonna explain basically what needs to be done. Sorry, that's the doorbell of the dog.
Yeah, I mean, but then I'm not sure that's necessarily the problem, because, you know, kernel CI is a mix of, yeah, like Collabora, Bay Libre, all these kinds of ones where we sort of pay proper attention to it and maintain it professionally. But then it is also a ton of labs in people's garages. Like, you know, Kevin Hillman ran one for ages, and that's how all of a lot of them run Lava, a bunch of them run PyBoost and stuff like that. And it's not that they haven't been able to put the infrastructure together for power control and UART and all of that, because they have that and it works. So it's about, you know, it lives in their garage, and when they go on holiday for a week, the power goes off and you don't have results for a week. So I don't think, like, yeah, having bare metal, like, really, or B2C or whatever, like, really easily available for everyone is great, but I don't see how that solves our reliability issue.
Well, this is true that if you can emulate your hardware, that's the best. But then, like, for driver development, I don't see how. I mean, there are some things you can test, but then realistically, like, most regressions that we get are not in the common code, right? I mean, Daniel Vetter would probably say the opposite. So maybe I'm wrong, but at least there's a lot of problems that are very driver specific, and you just need a ton of hardware. And I don't see who else would be maintaining things except the project owners.
But Daniel, the one thing I don't understand in your argument is how different would that be if we were to run QEMU on the freshly compiled kernel just to make sure that the kernel boots, and probably just spin up some kind of DRM video card we can do that really quickly with the infrastructure we have in place, with the runners that we already have. It's just one extra job that we're running. How would that be a problem not to use kernel CI?
Yeah, no, I don't. I think that's a perfectly fine and good thing to do. It's just about how useful it is to, test the VKMS probes, right? When you're working on a Nouveau tree.
But if you're working on a Nouveau tree, then you need to have a form that is dedicated to Nouveau. Who is responsible for that? I don't know.
Yeah,
but
exactly.
We need to have people there. And it won't be me for what it was.
Yeah, I don't see any other way than this, than having people being responsible, and then maybe at some point, like getting the farm hosted more professionally. But then whenever professional come into play, it means that they're going to do something else also. And so, I mean, there's going to be issues that indeed the farm is down and we need to react. So one thing that I was thinking about is we could have some like a watchdog. Basically, you have, I think it's 24 hours to give results, and otherwise the job gets cancelled and the pipeline is aborted. But what we could say is that, like using a bot, just check if the farm has not, answered in, let's say, 2 hours. Then the runners, some fake runners, are going to run and just do one thing, which is saying basically, yeah, everything is good. You pretend the farm said yes, and then that's what it is. Like, if the farm is away, then the farm is away. There's no concept of warning in GitLab. That's annoying. But at least it would not block for too long.
Why are you trying to put some complex behavior when you already have everything in place? Let's say if the Nouveau farm that we have in place is not reliable enough, then we need to have another Nouveau farm from the people who cares. And if they do not care enough to maintain their own Nouveau farm, then they can just disable the CI entirely. I mean, the point is for my subsystem, which is input, which is completely different, I'm planning on adding my own runner and maintaining my own runner for the various things that I need to be done there. And I'll be the one responsible for it. If it faults, I'm the one responsible for it.
Yeah, I guess again, missing context. I was thinking more about Mesa CI, where there's a lot of shared code between the drivers, and let's say a RADV developer is sending a merge request, and then there is the FreeDreno farm being down, but the FreeDreno should have been run because there were some changes to the NIA passes. Then, like, can we allow the farm being down to block CI, and then you like having to merge code to disable the farm is, I don't know, seems wrong to me.
But if the farm is down and regression is introduced, is the responsibility of the people maintaining the farm or the code of the subsystem that needs that person needs to actually be the one talking to the people responsible for the farm. I'm not sure we need to have some complex way of handling. Oh, if this farm is down, then we can use this one as a backup.
No. Then if you had a backup, then by using tags, then you just let the GitLab do the right thing, which is pick another runner with the same tag. What I'm saying is, if there are some machines that, if there are no farms available to run a job, then basically I would consider it as being a pass criteria. It's, well, fuck it. If I'm not available for testing, then I'm not going to block everything. Just like in real life, if you are going on vacation for a week, then you basically accept that there's going to be development done when you are away.
I would have a slightly different approach in which, like, by default, we would say that the farm is mandatory to pass. And if we realize that the farm is down way too often, we can put the job as marking warning only instead of allowed to fail.
But can allowed to fail. Yeah, that's how they allow. Yeah. Yeah, but then there's allowed to fail, as in allowed to fail to get scheduled, and then allowing the job to fail when it actually got run. Because when it got run, then there was no reason to allow it to fail. So I'm not sure. Like it seems to be conflating two things.
Not necessarily, because if your farm is not reliable enough to be ready all the time, to pass all the times, then we shouldn't put some burden on the infra to ensure that the farm, I mean, if the farm is not reliable enough, it's the people responsible for the farm, and their job is not mandatory anymore.
Well, I guess that works as long as you don't have 100 farms and a couple of hours of downtime per year per farm. Because then otherwise, like every farm basically would get. The number of merge requests that could be affected could still be in the tens or even 100 per year.
Not necessarily. I mean, right now we're gonna introduce the pipelines, and we're gonna, in the same way the Mesa pipeline was built up from scratch, we're adding things one by one, and when we deem them to be stable enough, then we mark them as mandatory. If they are not stable enough and if they're not reliable enough, then we're just gonna drop the thing from the farm and then from the CI and just tell the people, well, please do
Make
something
it better. Yeah. Well, I mean, the organic way is a pretty hard to argue with way. Sure. Sounds good.
I'm not super happy with that kind of policy because there's a lot of drivers that don't even have a single developer. And that would probably be the drivers that would benefit from the CI the most because they have the least amount of effort, developer time, and so on. So do we really want to put some additional burden that their farm should be like 100% perfect? And if it's not that they don't care, basically? Do we really want to send that message across?
The one thing that you have to keep in mind, sorry for saying it that way, is that currently the status quo is that there is no testing.
Yeah, sure. I mean, yeah, but
if we were to add those things, then we would need to have those people actually stepping up and say, hey, can somebody help me doing that? And then we can discuss about it. I'm not saying that we should not let people doing things and we should not help them. We can always reach the conclusion. But what I'm against is having an entire facility to account for failures and for all this kind of stuff, when basically it's more a social issue and more something like, yes, maybe we can reach to an agreement with that person.
I mean, it's not only social; it's also like practical. Some people are working in areas that don't have reliable internet or electricity, or just going on holidays and don't have access to their infrastructure, whatever that is, and things can fail. I mean, if you rely on someone that is basically working from home or a small office or whatever, you can't really expect it to run from a data center, basically.
Yes, but that person can reach out to other people in the admin team or in Free Desktop or in Intel or in AMD, and we can try to reach something where, like, maybe if it's a single board that needs to be powered up, we'd be happy to have one at home. I don't have a fiber connection, but whatever. We can always reach out to some kind of compromise. If that person is not able to run the CI by himself or by herself, that's perfectly fine. What I'm just saying is that I don't want us to have some weird complex mechanism to allow people to fail when actually, if that's important, then we need to put
redundancy.
Redundancy, as many boards as possible for those. Reach out to the. I mean, it's never just one. It's never just one people. I mean, the board has been built by somebody, and usually we can try to contact the manufacturer of the board and try to see if we can get some extra hardware to put in some places around the world where we would be able to have that.
Yeah, that was that's why I want to make it cheap to operate this testing farm, because then we can have more people around, and if one farm is down for whatever reason, then it's okay. But the problem is going to be that some farms are going to have unique hardware, and well, I accept what Benjamin was saying, that maybe what we need to do is just allow the jobs coming from these hardware to just fail. I'd rather have it that that it's failed to be allocated or to get started, but then if it is just allow fail, then that's better than nothing.
Yeah, I mean, allowing to fail or whatever was completely fine for me. The one thing that I wasn't really in agreement with was the fact that if people can't make a farm reliable, then we shouldn't even care about that farm. It's everything. It's basically all I was in disagreement with.
Yeah, I guess the solution for this is, if you can't get a farm reliable, just get more people to add, and then through the power of probability, it's way less likely that 2 or n farms are going to be down at the same time.
The just part is the difficult one.
Yes.
In what you said.
Yes. Just need to get people to care. But I mean, like, I don't know, developers have so much hardware at home, but you need to get them to care.
I mean, what I'm saying this is a social issue, in that person should never be alone in its even if it's just a hobbyist. There are people who care enough for the entire infrastructure, and could it be Collabora, could it be even Red Hat, or this kind of people, and we can still reach out. They can still reach out to, for instance, the admins of GitLab or Martin or anyone, and we can try to figure out something. We can always. Yeah, go ahead.
Yeah, we're generally pretty happy to take new stuff into the Collabora farm, although it has to wait until we've rebuilt our office because it's got too big now. The other thing is, yeah, the actual life expectancy of individual boards is pretty depressing. So we don't do it for less than 3 boards, to be honest, because our experience with trying to do it on single boards is that you get maybe a year out of it, and then it dies and it's not really easily fixable, and you've sort of burnt all this time trying to get it set up and get it vaguely reliable, and then a capacitor goes and that's it.
Agreed to this. That if you don't have like a way to replace the hardware, then that you cannot be reliable.
But again, not being reliable, and if you have the job marked as allowed to fail, doesn't mean that you're gonna be kicked out of the CI. It just means that it's gonna be more work for the maintainers for the maintainer of those boards to actually look at the jobs.
Mm-hmm.
But I like the way the Mesa CI is working right now. I mean, it took some time to ramp up, but at some point when we realized that there is something wrong in one of the machines, we just disabled the machine in the CI. And there is a new patch that is added, which says, well, just disable this one because it's flaky enough. And it could be that you just send there is a patch like, okay, this maintainer is on vacation, his power at home just blew up or whatever. We just disable the farm for the time it's restored.
Well, but have you been contributing to Mesa a lot? Because at least some of the Mesa developers I know are very, very sour about how often, you know, merge fails to merge because of whatever fucking reason. And so
yeah, they're wrong. We've covered in Grafana, they're wrong.
And plus, I'm most of the time responsible for those failures
Okay.
with GitLab.
Okay, well then, fair enough. Yeah, but someone has to care, that's for sure. Like, it's not, oh, I expose machines and then that's it. But then, even then, let's say that, I mean, I care and I want to have the machines exposed and I want to provide some value to developers. If I spend more than half an hour a day on maintaining the farm, that starts being, you know, an acceptable cost. And if you're on call 24/7, that's also something that is pretty bad. So this is why I was thinking that having a way to just be like, well, the thing is down, okay, I'll just report. And this might be what I'm going to do for my farm, actually, just have a automated thing in the cloud that just, when my farm is down, then I'll just accept everything. And that's, I think it's relatively easy to do, and that would be something that is purely local to my farm.
But then I don't really understand how this is different from, you know, you said it was a pretty hard no for the kernel CI model before, but now we're back to, you know, hours of latency and completely advisory results, which might not ever arrive. So,
well, the difference would be that if after running my farm says no, there is a regression, at least it would block pre-merge. Whereas if you allow it to fail, then it wouldn't block pre-merge. And then, yeah, the farm needs to be available for the testing you want to do. That do agree. And that's actually one big concern that we have. How are we going to integrate with Mesa CI? Because the 30-minute latency requirement is pretty difficult to reach. Because not only is you need to do the testing in 30 minutes, but on top of this, you need to have been fully idle, or you need to be able to run in, let's say, 10 minutes. So for instance, I have one machine that is extremely fast, so I can run DQP in about 10 minutes. Very good. So that means that even if there are multiple jobs running already on it, then it's going to be able to go quickly to this new, Mesa March testing. But then when it's running traces, it won't be able to do this. So I mean, at some point, I'll actually have to work on making, you know, like resumable jobs, so you can just stop, preempt it, and do a more important thing, and then go back. Otherwise, we're screwed. And latency is a big issue, basically.
But that's also assuming that the maintainer cares about the results of the pipeline, right?
Well, if they don't, then what's the point of testing?
There are, I mean, if you consider that the results for the individual machines is flocky or not, you can always mark the job as allowed to fail, and have the ones that you actually care, the ones that are mechanical, that are reliable enough to be the ones that are required for the pipelines. But I do not think that we are going to have that we're going to start enforcing the CI as soon as it's in. For the
Yeah, I do agree with this. That it needs to be more organic, and just like a new developer needs to prove themselves, the farm needs to prove itself. Yeah, absolutely. I think it's getting quite late now, so we are already over time. Do you have some opens you would like to talk about? So for me, there was one thing that we didn't speak about for the traces that could be interesting. That's what to do with March, and if a frame has changed, what's the expected workflow there that we would like to have. But does anyone else have something that they would like to talk about? Is the topic that I proposed interesting to someone, or is this something that we should just do outside of this meeting?
I mean, it's definitely interesting, but I'm not sure anyone has any good ideas about it.
Yeah. Well, I mean, the only thing that we could do is basically have 2 stages of running, but that's a little crazy. Like, you run it once, you check the outputs, and then if there is no changes, then yeah, you can merge. Otherwise, you need to go back and then have someone review the new frames and potentially change the reference frames or something, and then ask again. But that's wasting a lot of time. I don't know.
Yeah, it is, but that's the best we have right now. You know, you get in the EMR, you see that it fails, you get shown the traces side by side, and then if they're good, then resubmit with the same expectations. But that is, yeah, again, assuming that they're actually static rather than some kind of unknowable variance every run.
Yeah, but then for this, then if we model the noise, then you add the new frame to the acceptable, to the pool of frames that are acceptable, and then ask to regenerate this reference frame. Oh, but that's also one thing. Then that means we need to store the reference frame outside of Mesa, which anyway is the case. So I guess, yeah, it's no problem. That's what I like with the idea of saying if a frame is acceptable, it shouldn't be tied to the Mesa version. It should just look from a human perspective, is it good or not? And then we can have the same reference frame for every Mesa version, and potentially even every GPU and manufacturer. That would be simplifying everything. So we have been working on a website that allows you to do this sort of review. I hope that we'll be able to show you guys how, like, basically our experiment. Everything we do in this field is research. So research and development, maybe. So I guess we just try and then see and give feedback, and then yeah, basically that's all I can see. Just need to try. Okay, then I guess that's it for me.
Thank you, Martin. Thanks all for attending. The next session will be in about an hour, so let's take a short bio break. And we are back with the second workshop of the day, SSA-based register allocation, led by Connor Abbott and Daniel Schurman. Connor, Daniel, the stage is yours.
Hello guys, and welcome to our workshop. I think this will be way less formal than yesterday, so
yeah, we're not.
We'll have a chat together. We will go over some stuff we prepared. We wanted actually to enable our camera, but our Wi-Fi connection on this device is kind of poor, so don't want to risk it now to drop out. So we probably will just leave it turned off. Yeah. Do you want to wait for Jason?
I don't know. I presumably he's just getting out of his talk now.
So for the...
Oh, Rob is asking. Yeah. He's here already.
For the structure of this workshop, we thought that we will probably go through the algorithm again, this time a bit more slowly, or in the speed that everyone can follow it, and we can also see if there are questions. If we skimmed through something too quickly yesterday, you can ask questions all the time. Then we will probably...
We'll talk about a few other bits and pieces that we didn't get to talk about that are kind of relevant for ICO and IR3. And if there was any questions from the IR3 register allocation review that people still didn't understand, we can also go through the code, and probably for ICO too. We have, I think Daniel has the code open here. Yeah, so the reason I originally did this talk was that, that I originally wanted to do this talk was that people were asking me on, when reviewing the IR3 register allocator, like, hey, do you have any resources that explain the basics of this, like any overview? And there's all of the existing resources are started off with like, oh, this is the definition of a chordal graph, and this is a perfect coloring, and then hand waved away all of the line frame splitting, the details of line frame splitting. So I hope that this will be useful. And so if there's something that can be done more effectively in person than in code review, which is always a little tougher for big complicated things, then we can also do that here.
And then we can also lose a few words on register allocation validation, and eventually maybe present even a path towards SSA-based register allocation without doing it directly on SSA. If you understand the theory behind it, then you might already figure there is a way to do this SSA-based register allocation style on after translating out of SSA. We will maybe briefly talk about it just to give the opportunity, if you're interested, to in converting an existing register data to be able to do that. Yeah, please let us know if our connection is bad, because I already see that red light there. Or if you don't understand anything, you can also at any time basically unmute yourself and ask a question. Otherwise, I think we just jump into it.
Should we wait for Jason? Because he said he was interested.
Sorry, I didn't get that.
I was just asking, should we wait for Jason?
Should we, Jake?
I think he's doing his own breakout on ray tracing, which is a little sad because I know he really wanted to be in here.
It's not right now. he just finished his talk like a couple of minutes ago, I think.
Yeah, I think he's going to put one together, but later.
Oh, okay, later. I misread that then. Okay.
He just joined. Hi,
Okay.
Jason.
Hello. What am I putting together later?
We were more in the introduction, so you didn't really miss anything. Okay. So the idea is that we go over the algorithm once again, more slowly, and to allow asking questions and see if everything is clear. Yeah. So
let's skip the SSA form stuff.
Yeah, I think.
Let's skip the background.
I hope SSA is clear for everyone, and also the deconstruction. I assume that it's pretty clear that you have to insert copies at the control flow edges. Also, register location itself should be a topic that is clear, and the idea why.
Okay, yeah, so let's start here, I guess. Yeah, so hopefully the kill flags thing is pretty clear. The way the actual algorithm works is very simple. You just walk backwards and keeping track of what's live, and then the first time something pops up while walking backwards, you add the kill flag to it. That was one of the most straightforward parts when I was implementing it. Didn't even bother looking at what Echo did because it seemed pretty straightforward.
Yeah, it just indicates that the variable is no longer used after this moment.
The only reason I really put it in here is it's an important data structure wise, like what actual data structure you use. So it's kind of different from, for example, linear scan, where you keep track of the ranges instead. And then this is like the core algorithm that stays the same pretty much throughout the entire thing, although it gets kind of wonky as soon as you start to do line splitting. The whole idea of like having this register file, and for each register keeping track of whether it's available or in use by some value is kind of the core idea here. And that gets way more complicated and tricky as you add more and more stuff on top of it. But the basic idea stays the same. Just add kill flags. Use the kill flags to figure out if you need to remove it from the file, and then pick something from the available things. And all of the secret sauce, all the hard parts, is going to be put in pick fizzers, which I'm thinking now I should have called it getreg, because that's what Echo and IR3 call it. That's kind of a mistake, but whatever.
Yeah, so for the actual algorithm to pick a physical register, there's plenty of choices. For example, we use in Echo we use best fit at the moment, and in IR3 they use some round robin to figure the register, which is likely a good fit.
Yeah, it works better because we have these NOPs. So unlike in the RDNA2 we have, but unlike in the original AMD instruction, there's a delay between writing and reading a register. So
pipeline stalls.
So the round robin does a really good job at avoiding that. I know in the graph calling algorithm that was originally proposed, the round robin, but round robin actually does even better with this, because rather than doing round robin on some random order picked by the core graph calling algorithm, you're doing round robin on the actual source code order, which is what you really want. So when I did that, it went from being net negative in terms of NOPs into net positive.
So are there questions up to this point?
Hi, it's Tim Renouf here. I was just wondering about the round robin thing, because something that was pointed out in one of the papers about this is that round robin gives you a chance to do better in post-RA scheduling. Does ACO do any post-RA scheduling that could take advantage of that?
So ACO
not
doesn't
yet.
but IR3 does. It does do post-RI scheduling. And like I said, doing a round robin made it dramatically better. So I started out with the best fit because I was just copying from ACO, and then IR3, and then I changed it to round robin once I got the register pressure estimation working, and then that improved the quality of post-RI scheduling dramatically from worse than the original, which was doing round robin but on graph coloring, to even better than the original, which I'm hypothesizing is because I'm doing round robin in the source code order, which is going to be better.
Yeah, and I take your point about on RDNA that you have those pipelines installed, so round robin helps you on that as well.
Yeah. I think in ACO, someone's working, Timur is working on the post-RA scheduler.
Yeah, Timur wrote some post-RA scheduler that's a bit work in progress and needs more refinement and stuff, but we will definitely look into that again. And then we might also switch to round robin, but yeah, that's...
By the way, what's your IRC nickname? Because I would be interested in talking to you about your post-RA scheduler.
Yeah. Yes.
Then let's look into handling control flow, because here stuff gets more interesting.
I assume most people know the classic data flow algorithm. Again, this is something you can find online, described many different sources. And it's just the data structure there is just the live in and live out bit set. I think that's how both ACO and IR3 handle it. And in addition, you have these kill flags. So now you do the same like dance of walking backwards, but start out with the live out set instead of with nothing.
Also keep in mind that now a variable can have multiple kill flags in different blocks. Like it can be killed once in the then branch leg, and then it can be killed again in the else branch leg.
And in a loop, it's important to note that a variable can have no kill flag at all, and it can just be killed in the end of the loop, kind of. If a variable is defined outside of the loop and then used inside the loop. Dominance, hopefully everyone's, we kind of assume you know SSA.
So can you?
Yeah.
Going back to liveness and kill flags, maybe you said this and I missed it, but how do you handle the weirdness around disabled channels for, say, SGPRs?
So SGPRs don't have disabled channels. That's the thing, because they're scalable.
It's alive, even if it's not, like, it's alive in portions of the IR where if you just look at the classic, like, node-based control flow graph, it looks dead.
Yeah, so the way Echo handles that, well, do you want to talk about that?
Yeah, so in Echo we have a linear and a logical control flow graph. So we clearly we basically do two different sets of live in and live out variables. One's that and the uniform values basically follow the linear control flow graph, and the live in and live out sets are along the edges of the linear control flow graph, and the VGPRs are handled along the logical control flow graph. And
so fee nodes and stuff, for example, might have different numbers of arguments depending upon their whether it's like a logical fee or a linear fee.
Yeah. So the second point, I think, yeah, Connor can, I think, better talk about if you have implicit control flow instructions. So not having this linear control flow graph and still be able to, yeah.
That's a bit tricky. Honestly, I don't remember exactly how it works on Intel, but I remember if you watch the talk a bit later, I mentioned how because these phi nodes are supposed to happen along the control flow edge, if you have a critical edge, then it becomes a problem because you can't insert the fixed code, and so you need to insert an edge, a block along that edge. But the problem is that these like linear edges that you add to model what the machine actually does, well, those are critical edges. So if you just add the edge from the if to the else in your simple if-else, then it's going to be a critical edge. And in ACO, they can kind of get around that. And there's a nice graph Daniel tried to find again because you have the hardware has complete control. You have complete control over the hardware. So you just go and insert a bunch of empty blocks.
Yeah.
And then you get a picture like this.
Yeah, so what you can see here is that divergent branching in ACO is actually done as two branches, one for the then and another one for the else. And we remove both critical edges by inserting like linear extra blocks.
And those linear blocks don't actually correspond to anything in the original shader. They're just there in case, well, the invert thing inverts the exec mask, but the then and else linear blocks are just there to insert any extra, to hold any extra copies you might need to generate in RA if they're phi nodes.
Yeah, that makes sense.
So if it's possible, like the way normally with implicit control flow, you only have the bottom picture. So if you can insert, so that on the bottom picture with the logical then and else, the linear edge is just a single edge from the then to the else, which is then a critical edge. So if you can somehow insert a basic block between them, which is basically would be with like no mask enabled, with nothing enabled before turning off the exec mask and then before turning it on for the else, then you can get around that problem. But otherwise, you have to, I don't know, resort to some hacks.
There actually is some hack possible, and we can get to that later, I think.
Yeah, the hack I did for IR3.
So, or just to phrase the idea quickly, it's that you copy back the uniform values to their original position if you had a life range split within the branch.
Within the then.
And there's
the then branch.
Yeah, and there's some theory behind it that it's always possible. Yeah, but we can also discuss that a bit later, I think, and continue on the algorithm.
Okay. Yeah, for us, unfortunately, we don't have a clean split between SGPO and VGPO unless we went out of our way to artificially create one.
Yeah, so you would probably need to split liveness into 2 bits, which you probably already do, I imagine. Like whether something is live in the active lanes versus whether it's only live in the inactive lanes, and then but the problem with is that if something is live with only the inactive lanes, multiple things can be sharing the same register, so things get a bit hairy.
Yeah, and the other thing is that we can have even logical things that still interfere in the physical control flow graph because we don't have, because of the crazy striding stuff that we do, if you have, say, a 32-bit thing and a 16-bit thing, they may actually have different sets of channels overlapping.
Right, so then in that case,
sort of physical.
I guess what you have to do is somehow keep track of at each point for each VEC8, like what the channel stride is, whether it's not being used by anything, it is being used by an inactive thing, and the channel stride is X, and you may only use the X for active things, or
So
it's
yeah,
live.
I've gone so figuring out the liveness isn't too bad, and I've gone about like some approaches where we keep track of strides and we try to match similarly strided things on top of each other, and it works for the purposes of interference. But when I'm thinking about how to deal with like phi node resolution and where do you place the phi nodes, what happens if you move one of those things, I don't have a good idea how to do that yet. The fact that most GPUs have vGPRs that cannot interfere across channels really helps with that problem.
Yeah, and you can add a few hacks for the remaining scenarios, like subgroup operations, where you do have that, but the linear,
I have been wondering about is your
VGPR
example sort of assumes like a uniform register file if you have available registers and you're doling them out, but does that work when you have SGPRs and VGPRs? Are those just two sets of registers? How does that work for like half floats versus doubles?
So for SGPRs and VGPRs, it's very simple. You just keep track of the SGPR pressure and the VGPR pressure. They're just two separate register files, and you can pretty easily extend this. So instead of a single available set, you have like a available set per register file. That's actually the easy part. Versus the doubles thing and whatnot, that's where line range splitting comes in, which is the next part of the talk.
So there's a clear distinction. So doubles are basically vector registers, at least for Radian, because they just occupy two registers. For half floats, that's a bit more tricky because they occupy half a register, and then is the question, what about the other half? Do we pretend that it needs the full register, or do we want to reuse that for something else? And yeah, we basically wrote a hack on top of our register allocator to handle that, but the different idea would be to just use it per byte, your register file, or there's different solutions. So in the end, I think that's more an implementation detail than actually something affecting the general idea or something. Yeah. We can have a look at what comes next. So dominance, we already talked about that. Basically, in source code order, in an SSA, you have dominance properties satisfied. And here we see that you can get these two kill flags on the then branch lag and also in the else branch lag.
I think in this one, it's used in a loop, so it doesn't even have a kill flag at all, which is kind of what I was mentioning.
No, then you would have no kill flag in the then branch either.
Because
on the right hand, in the else.
So I was trying to mention the two. I was trying to, I think with this one, I was going for the two scenarios of like it can have a kill flag, or it can just be killed at the end of the loop.
Yeah, either way.
And then I went over the proof of correctness of this, like dominance order thing, pretty quickly. So if anyone has any questions, and this is kind of the key part of like why it's called tree scan, like why this like works at all and doesn't blow up in your face. So if anyone has any questions about that, about like why it's correct and why when we visit the beginning of the block, everything is already in a separate register and already visited.
Yeah, I think so. The key point to take away is that at the beginning of each block, you iterate all live in variables and fill your register file with where the variables already are. And there's only two ways how you can have incoming variables in your register file at the beginning of the block, and that's either they are live in, that means they are live out at the immediate dominator, or they are from a fee node. So it's only these two options, and the live ins already have a register, and that's the same register no matter from which path the control flow comes. And then there's the fee nodes, and these variables can be in different registers depending on the control flow graph, depending on the control the path takes. So
oh, and one thing I think I forgot to mention, I'm just thinking about this now. The reason, so this algorithm, actually, we didn't even treat fee nodes as special at all here, and it still works. And the reason why is that we treat fee nodes, you have to treat fee nodes as special in the liveness analysis pass. Because you have to treat fee node sources, again, as being read at the end of the predecessor block. And then they sort of kill, or they can anyways, kill that value. And you have to be a bit careful about that.
Yeah, so what happens is that you actually just pick any free register for your fee nodes, and then hope that your sources, the sources of the fee node, have the same register. That means that you get away without any copying of registers. It's just, yeah, then it's already there in the correct register. Or if you're not so lucky, then your sources of the fee node have a different register than the destination. And this means you have to implement a copy from one register to the other register in the predecessor or along the edge from the predecessor block.
Oh, and one thing I forgot to mention, the fee nodes are not special at all in this, but once you start to do live frame splitting, then fee nodes do have to become special, because they do become special because you don't insert parallel copies. You can't insert parallel copies before them. They have to stay at the beginning, and you kind of have to allocate them all in parallel. So you can do basically the same shuffle code, but then the shuffles are basically free. Not really free, because you might have to insert more copies for the fees, but you basically just ignore it. And then at the very end, you have the initial state of the register file, including all of the fee nodes and all of the live-ins, and then you just go and assign the destinations for fee nodes all at once.
Are there questions about this part? I hope we didn't explain it too confusing.
Yeah.
Did we drop or no? Okay, that sounds like
hopefully
like nobody understood.
Either everyone understood everything or no one understood anything, and it's usually the second one.
Okay, you really have to tell if that's unclear.
Yeah, because there's no, we can't really read the room, so there's no way to like look and see if everyone is totally lost.
I'm still good.
Cool. So here's then we had this example about the fee nodes.
Yeah.
This was with swapping. So Connor said that fee nodes happen in parallel. This does not mean that you have to allocate the registers in parallel. You can just pick one by one. Yeah, keep in mind that live range splits there, if these need to happen, then they are a bit more complicated. But the idea of how the fee node is executed, so to speak, is that they happen in parallel. So if you assign them the registers, like in this example, there you can see that E1 gets register 0 and the C gets R1. And this is like already Connor said in the presentation, it's fine for the then branch, because you can see on both phi nodes that from the if, they also, A comes from R0 and D comes from R1. So there's no copy needed. The incoming value is already in the correct register. But coming from the L side, the E0 value resides in R1 and the A value resides in R0. So they are in the wrong registers and need to be copied to the destination of the phi. And this has to happen in parallel, because all the phi nodes are basically executed in parallel, or the values are read in parallel. So in this case, we have to copy R1 to R0 and R0 to R1, and this needs a swap.
Yeah, and I think the reason I chose this example is that if you like work at it with paper and pencil, you can kind of see that it's actually impossible to allocate this program without swaps using only 2 registers. So this whole like phi nodes execute in parallel is not just like a thing we made up. It's kind of what makes the whole thing possible in a way.
And let me tell you, so much it actually happens in practice. I don't know why, but some people like to program like that. So it really occurs in practical shaders. And but also this can happen on accident. So the big difference between SSA-based register allocation and the classical register allocation is that you don't really know in advance, which variables should go into the same register. So in the classical register allocation approach, there is like the E1 would be the same variable written in the then and in the else branch, and C would be the same variable and not 3 different ones. So it's clear that they kind of must get the same register. On SSA-based register allocation, you don't know that, and your register allocator just has to try to give them the same register. But if you want to make this perfectly, you are definitely in an NP-hard terrain. And if you do that heuristically, you might end up with just bad luck and need to insert swaps and a few copies more. So if you have a swap instruction in your architecture, that's cool. And if you don't, then, well,
sorry.
You basically end up with, if you only swap 2 instructions, that's the same amount as you need if you have an extra register, right? Then you also need 3 instructions.
Yeah.
If you have chains of swap or cycles, then an extra register would be good. I mean, you can, it depends on how advanced you make the register allocator. You can check if there's a free register available and hand this over and try to use that to resolve these cycles. And this brings us to the resolving of the phi nodes.
Yeah, so this slide was more of a rather than examples, like how to do it in general. And I really sped over this because I thought we would run out of time, even though we actually didn't, kind of wound up early. So here is a place that if anyone wants to know like more about the details of the algorithm, they can ask away. It's again very similar to the from SSA and NER.
I wonder if this is actually also an NP-hard problem, but you always have this very short very low number of
I don't think
copies.
I think the simple version isn't NP complete. Like, I think you can prove that the version in that paper gives you the minimum number of copies.
But is this linear?
Linear time?
Yeah.
Yeah, the algorithm in the Boston paper.
True.
I think this part isn't the hard part. But the funny thing is that in practice, this algorithm can become really complicated because right now I'm just talking about the simple case, but in the more complicated case, where you have different kinds of registers and whatnot, it turns out to be a good idea to just have a parallel copy instruction that can basically copy anything to anything. And that simplifies a bunch of other parts of the compiler. And then you can put all the complexities about like, which instruction do I use, which weird swizzle do I use, and so on, into this pass. And you can use it for phi nodes. I think later I mentioned you can use it for splits and collects. And the parallel copies you create with live range splitting. So it's really versatile and allows you to put all of those fiddly like copy details into one pass.
So, but the general idea is that you have a bunch of copies that need to happen in parallel in the semantics, and you try to find a sequence of instructions which has the exact same semantics as if it happens in parallel. So you can quickly think about that. It's fairly straightforward that you have to follow an order how to copy one register to the other, so that you never overwrite something that you still need. So that's the idea. And you might end up with a cycle at the end, or with multiple cycles, and then these cycles are a series of swap instructions or XORs. We also have the statement here that you need to consider affinities. That is,
I think we touched on that before, right?
We already touched on that. So it's best if you avoid that the fees. If the fee destination is a different register than the sources, then you don't need a copy at all, because the value already is in the correct register. So that's all this affinity stuff about, and you can try to make it basically infinitely smart in your register allocator to try to always match the fee sources with the destination, but it will still not always work out.
So yeah, in a traditional graph coloring register allocator, the hill you die on, the thing that kind of always sucks is you just pick the wrong like allocation order, and then you just run out of registers. And then that always winds up being a problem, and you have tons of heuristics to sort of tune that and so on. And try and fix that and try to do live range splitting. And then here, the problem becomes, oh my God, we're inserting too many copies. Why?
Yeah, I just, on Monday, I created a merge request that does tune the affinities and the echo slightly. And I think it removes like 2% of all copy instructions. Or that's very sensitive in the register allocator, how you handle affinities and this kind of stuff. It has a really big impact on the final outcome. That brings us to live range splitting. Live range splitting basically is the solution to all constraints, all assumptions. It resolves all assumptions that were taken in the previous papers about SSI-based register allocation, where they assume that every variable has a size of 1. So, and there's no pre-coloring and no whatsoever, and every instruction can use the same registers and stuff like that. And the live range splitting basically helps to resolve all these issues, I think all. So if you have pre-coloring, you can resolve that with live range splits. If you have vectors, you can resolve it with that. So yeah, it's the hammer to solve, to make it fit.
It's the hammer we have, and then everything kind of looks like a nail. This was also one of the main reasons I wanted to do this talk, because again, if someone asks like, well, is there an overview on how live range splitting works in ACO and IR3? Again, the answer is no. So all the papers on SSA-based register allocation just kind of hand wave their way around this and say stuff like, just insert a parallel copy instruction for every live value in between every instruction, and then the graph is portal again. And you're like, but that would kill performance.
Yeah, I think there's actually, I only remember one paper which does a live range splitting algorithm. That's the puzzle solving paper from Fernando Pereira. And he assumes that every vector is a power of 2 in size, and that simplifies stuff a lot. It simplifies stuff so much that we just cannot use it. As soon as you have vec3 or you have unaligned or both vectors, then it all falls apart, and you have to figure, like,
it's probably NP hard as soon as you add those in.
Yeah.
How much the minimum splitting problem.
I mean, I hope the example is more or less clear, that you might end up in a situation where there's where there is enough space in the register file, but not for your variable.
Not contiguous.
Yeah, not contiguous, it's scattered, and you have to make space that is contiguous.
So yeah, it's like the fragmentation in like a memory allocator or something like that, except that here we have the tools to actually move things around and fix it, the fragmentation kind of.
Yeah, and in this example here, we just move the one register away, and then we have enough space. But there is this worst case scenario, and I only want to mention it briefly here. Here in this example, we just have one free register at the beginning, one at the end, and in between we have only vec2, so we cannot move a single variable away to make space. We would actually have to move every single variable that is in the register file. And just for how probable is this even? And I can tell you that in ACO, this happens exactly once in the whole CTS, that a bit tries to force this scenario by loading a bunch of vec3, I think. Like the whole register file is full of that. And that's the only situation where we ever needed that. And to fix our broken CTS test, Reese implemented a small algorithm that just moves every variable to the beginning of the register file. But that's really such a worst case scenario. You will likely never encounter this in any real world application ever. But
go ahead. I'll let you finish what you're saying, then I have 2 questions.
Sure.
Yeah. What were you gonna say?
Yeah, just that this likely never happened. Did I want to add more? I don't think so.
Okay.
I was done.
Okay. So first question: Have you experimented with artificially slightly decreasing the size of your register file to make this less likely?
To make it less likely, you mean like overestimating the number of variables we need?
Yeah, by like 1 register or something to give you just a little
so
bit.
ACO does kind of do that, where, well, it does it on the fly. So like rather when they have a sort of clever recursive algorithm that tries to use less moves, and when that fails, rather than doing this, shuffle everything, they just bump up the size of the register file because of the whole dynamic register sharing thing.
So first,
does that have any interaction with the occupancy cliff edges? Because you know, it seems to me that there's no point trying to allocate into 62 registers because 64 gives you the same occupancy. So you would kind of round up anyway, wouldn't you?
Yeah, I mean, if you're near the edge, then yeah, you just have to suck it up and just move everything, because this whole point of this SSA-based register allocation is that you don't have to spill. But fortunately, so it is kind of unfortunate if you're on the edge and then you just kind of have to move up. But yeah, so in ACO and IR3, the way it works is that we calculate the register pressure, and then from the register pressure, we calculate the demand that's possible, assuming that we just allocate everything as tightly as possible. And then from that, we go and calculate the real register pressure. So we do this kind of thing you mentioned where if we can bump up the demand by a few extra registers to have the same occupancy, then we will do that. So this case doesn't come up unless your register pressure happens to be exactly at that limit, usually.
It would be interesting to figure if you can calculate a minimum number of extra registers you need to never get into this situation, or if this is possible. I think this will be either too large to be feasible, or it just doesn't work out. But another thing to note is that in normal real world applications, you always have enough single scalar variables next to each other that you can always move these scalar variables into empty slots and have space. So the practical worst case is that you have to move size of your vector variables. Yeah. That's what happens in practice.
And the other thing to note is that most of the time in the backend, you are immediately creating a vector when when you need to, let's say, have a texture instruction. You just create a vector immediately before it, and then in a load instruction, you split the vector immediately after in instruction selection, typically, and then if you keep that around, if you keep that split vector and create vector around, then the amount of time when there's a vector register in the file is very, very small. This only really becomes a problem when your pre-RA scheduler moves things around, or when you optimize a split and then collect into the original thing. Which I think ACO does that for other reasons, which is maybe why you ran into this problem in the first place. It kind of sucks because if your pre-RA scheduler does that, and if you don't have this optimization of detecting a split and then a collect and then just returning the original vector, then you're never going to have more than 1 or 2 live vectors at the same time, and then you pretty much never run into this in practice. But there's no way in theory to go through your entire allocator and your entire backend and just prove that this will never happen.
Our pre-RA scheduler has some can create some entertaining shaders sometimes. Create the payloads for 16 texture instructions and then fire the texture instructions.
Yeah, so that's exactly the scenario where this kind of becomes an issue.
So the other question that I was going to ask is, have you considered, am I still here?
Yeah.
Okay, sorry, my display blanked, and so I don't know what happened. Have you considered, if you hit this scenario, instead just move the first component of V0 out of the way, and then recollect it back later?
I actually started out the IR3 register allocator assuming that I would do this, and then it became a giant mess. Because I started around the time I started it, Riz was implementing this special case, and I was like, I can just avoid it, right? The problem is that the data structure then becomes way, way more complicated because consider that instructions can have multiple vector sources, and then those sources all have to be aligned. So like your, I don't know, texture instruction, or like a store instruction that takes both a descriptor and a vector value, for example, on AMD or something like that. So you still kind of have this problem because let's say you coalesce the first source, and then yay, you can just move whatever components, you don't have to care about this. But then once you've coalesced it, it's there, and you can't break it up again in order to coalesce the second source. And when you allocate the destination, you also can't uncoalesce those sources. So again, it's this case where like you in theory don't need the backup, but how the hell are you going to actually prove that like whatever heuristic you came up with like actually does this successfully?
Yeah, because you have, at least on our hardware, you have potentially 3 vectors that all have to be vectors at the time the instruction executes, because some sends can have 2 vector sources and a vector destination. So yeah, okay, that makes sense. I just, like, when I was looking at this, it's like, okay, there's an obvious solution to this. I'm sure there's a reason they're not doing this. I don't know what it is.
I tried real hard.
Yeah. We also discussed this like several times and gave up on it. But it's so it's so rare that I think it's not really worth the time that you spend on it to improve this one edge case that actually never happens.
So you implement this kind of shitty algorithm, and then at least you sleep soundly at night that your register allocator won't fall apart.
And you pass the CTS.
So the code you compile, presumably it never has calls in.
It never has calls. So calls, well, we haven't implemented shader calls, yeah, but that's basically the same sort of shenanigans.
Yeah, that's what I was thinking. Yeah.
So when Daniel mentioned never having preloaded, never having pre-colored registers, again, this is the solution. This is the hammer for your nail.
Yeah, but with the calls thing, is there a not with the fragmentation thing you're talking about here with the vectors, but with the call thing, is there some scope to kind of bias your register allocation to try and avoid the situation happening and avoid?
Yeah, so it would be similar to the affinities, the phi affinities, probably.
Yeah.
Yeah. We also use some kind of affinities for our vec3, vec4, and such instructions. So if we know that we will use these components later in a vector, we already try when assigning the register for the variables, we already try to align them next to each other so that we don't get overhead when we are at the actual create vector instruction. And something similar would be done if you want to call arguments in specific registers that you already try to use these register when the destination is written. So yeah, that's part of the heuristic to improve or to have less copies than in general.
Yeah. And another thing to note is that it's actually impossible, or it can become impossible if you want to have fixed registers that don't start at the beginning. Because if it doesn't start at the beginning, like if you try to fix R1, R2, and R3, well, what if the rest of your register file, what if the rest of the live values happen to be vec2s? And then there's like one hole at the beginning and one hole at the end, and then you just can't move it. So you really can't allocate it without spilling. So you have to be kind of careful with dealing with fixed registers.
So I think for us, we have fixed registers at the beginning, and we have fixed registers at the end. But the live ranges of the two never overlap.
Yeah.
But at the end is like.
Is that at the send message at the end?
So there's a requirement that the last message that leaves the EU has to be in high registers, or else there's a race.
Yeah, I think that's pretty
between
easy to
filling
handle. We
out
actually have something very similar in IR3 because we have these shader chaining thing where, kind of like on AMD, the vertex shader and the tessellation control shader are the same thing, but they're actually in separate binaries. The hardware has a magic instruction that one chains to the other, and then there's like an ABI in between them. So like some special magic control registers have to be in like R0, and then this one has to be in R1. But that's not hard to handle because first of all, you do the biasing thing that we were talking about of like trying to allocate it in this register at the definition. And then at the very end, well, the only thing that's live is your register. So you can just move it around however you want. And so you can, if you get to that last message and then it just happens to be that it got assigned to the wrong register, well, you can just move it.
Right, that makes sense.
Yeah, if your register file is empty, then this isn't a problem. We can get to the control flow handling with live range splits. That is, what happens if a variable gets split on one path of the control flow and not on another one? So that means that in this example, V1, after executing both branch legs, is when coming from the then branch is in a different register than coming from the else branch. And this is kind of tricky because you have to repair that. So sorry for the slide. Let's stick with this one. So I think it's obvious that after the branch, you want V1 again to be in the same register, no matter from which path the control flow took. So what ACO in this case does is create a new phi node and assign it, remove it from the live ins, because it's in this case not really a live in variable with one fixed register anymore, but it's like two different values coming from two different paths. So we create a phi node, and this phi node gets a register assigned whatever is available. We try to give it like either R1 or R2 in this case to match at least one of the edges and only have a copy on the other. So one solution is that you insert a copy in the else side to also move it to R2, or in the then branch, like you can just move it back to R1. So, but either of the two have to happen.
And the thing I was mentioning to Daniel is that actually, so there are these two approaches that you either you either rename all the SSA values and like keep SSA, or you have the uses of your value have different register than the definition and insert these copies with just physical registers, which is what IR3 does. But even if you do that, you can't just insert a copy at the end of the else branch in this example. Like it just doesn't work because, and I have like a whole long comment on IR3 explaining this, but that copy has to happen in parallel with copies for phi nodes, because phi nodes, again, the sources are considered to be live. So we need to swap a phi node source, and so if we want to say, let's say we want to move R2 back to R1 at the end of the if here, then there might be something else live in R1 that then needs to be moved to R2 because we happen to put the phi node there. And then that has to happen in parallel. So what you'd have to do is create a phi node with like physical arguments and physical destination, or what ACO does and just keep SSA alive. So it's a bit tricky. You can't just insert copies blindly.
Yeah. So the algorithm Echo does in principle is just a very straightforward SSA repairing algorithm. What IR3 does is just basically repair the register, and IR3 just remembers the register, and Echo, creates actual renames for the SSA values and repairs the SSA. Both have the same result and are in principle the same idea. It's just a question whether you want correct SSA after the register allocation, or if you don't care anymore about SSA after register allocation. So I think that's it so far about the...
Do we want to go into more detail on the live range splitting and the whole loops versus ifs question?
Yeah. So we didn't really... Here we only used a branch as an example, but it can also happen that you got a live range split.
Do we have the extra? Oh yeah, we have this extra slide on live range splitting.
Yeah. It can happen that you have the live range split in a loop. So what happens then, Connor?
Yeah, so let's go back to this slide. And let's say that, like, instead of an if else there, we have like a loop. We have a while loop, and the R1 gets moved to R2 in some like live range split in the middle of a loop. So what Echo does, well, do you want to talk about what Echo used to do versus what it does now?
No, I think.
So within an if, you can just create fee nodes on the fly, kind of, because once you visit a block, you've already visited all of its predecessors, and then you know what it got renamed to. But when you visit the header block of the loop, you might not have visited some of the predecessors before. So you sort of have to speculatively create fee nodes, or at least record somehow, like, so pick a register based on the things that were already visited, record, oh, these are the live registers at the beginning of this block, and then do the entire thing. And then once you get to the end of the loop, you compare, like, what are the registers now with what were the registers at the beginning. And then either insert fee nodes or just insert those like physical fee nodes. And if you insert real fee nodes like in Echo, then you have to go back through the entire loop and rewrite everything using that value back to the fee node.
Yeah, but let's just assume that we just insert the physical fee nodes or whatever at the beginning of the loop. Keep in mind that the register is already fixed. Like when you first visited the loop and handled the live in values at the loop header, then every live in already has a register. So when you do a live range split in the loop, then it's clear that the fee node has this original register, and you only change the sources of the fee. You cannot then pick a different register for your variable.
After you visit the loop.
Yeah, after you visited the loop, it will stay, like, it must go back to the original register. That your live range split will be copied back by inserting the fee node at the beginning of the header.
But then it actually turns into a copy at the end of the loop after when you lower fee nodes.
So, yeah, I hope this wasn't too complex now. What is this?
Oh yeah, but talking about the details of how you do live range splitting. We glossed over that, but so in the original algorithm, we processed the uses and then processed the destination, and they were kind of separate in separate loops, and we didn't have to intermix them. But as soon as we get to live range splitting, that's no longer the case, and things are no longer so simple because they kind of now interact with each other. So you need to consider that there are 3 types of values that you care about. First, uses that are killed, and live-through values, which includes uses which are not killed, which are basically treated the same as things that happen to be live through the instruction from the point of view of live-rank splitting, and then definitions. So the problem is, and one way to sort of describe it in the puzzle allocation paper that Daniel mentioned is you can imagine a 2 by n puzzle board where the width of the puzzle board is 2 and the height is the size of your register file. Killed uses can only go on the left because they end in the middle, and so the width 2 represents the state of the register file beforehand, and then the left-hand side represents the state of the register file before your instruction. The right-hand side represents the state of the register file after your instruction. And then killed uses can only go on the left, and you have to fill all of them in. Definitions only go on the right because they're only live after the instruction, and you have to fill those in. And then live-through values are live both before and after the instruction. So, and they have to be at the same value. You can't shuffle them during the instruction. So they have to be the same. And then you basically place these pieces on this puzzle board, and you want to find a solution to this puzzle which minimizes the number of killed uses and live through which differ from what they were before the instruction. And then after you solve this puzzle, then you, for everything that was different, for every killed use and live through that's different, you go and insert a parallel copy. And then those all have to happen at once because you basically decided the solution for your thing all at once, and then it has to be, the live values are live here, and then they're there, but we all decided how they were, you have to kind of decide where to put them at once. And then you insert this parallel copy instruction, and then the whole transfer graph thing takes care of actually turning it into hardware instructions.
Yeah, it sounded probably more complicated than it actually is. But in short, it's when you do the live range splitting and you move variables around, you have to keep in mind that this might be an operand that is just killed, or it might be a definition, a second definition of your instruction, and you have to take care a bit where you can move it if it really already exists, and at the point when you do the live range split, or if there's something else in the way, stuff like that. So
I think in IR3 we basically only support one definition per register file at the moment. And then the way it works is we keep the state of the register file beforehand.
You have the split instruction that has multiple definitions.
Oh, but ours doesn't, remember, because the whole register coalescing thing. I really wish it had multiple destinations. It would have made everything so much easier, but it does not. We keep the state of the register file beforehand, and also a split instruction is trivial because you can just always assign it to the same thing.
Yeah.
Anyways, so because we only support destination, we just look at the register file before the instruction, and then we shuffle things around to make space for the destination, record everything, insert our parallel copy instruction, and then allocate our destination to the hole that we basically made in that register file. But that kind of doesn't work if there's multiple destinations, because you kind of need to make multiple holes and remember where the previous hole was so that you don't kind of fill it again, or at least move it around. And I think ACO has a more complicated thing that can, in theory, handle multiple destinations.
Yeah.
Where you constantly switch back and forth to the state before and after the instruction.
But we block the register file to not move certain registers anymore. Anyways, yeah, don't really dare to ask if there are questions about this topic.
This is one of the nastier parts of a real world SSA-based allocator.
I wanted to talk with you about transitioning a existing classic register allocator to this SSA-based style without actually using SSA. So, but first, let me ask if there are questions about this live range splitting stuff.
I was wondering if there's any scope for, in some cases, just going back and changing the original allocation of that variable, but it sounds like that would be kind of rewinding and going a bit sort of taking the age of the universe.
Yes.
Yeah, I mean, this is where it becomes NP hard real quick, because that's basically like a backtracking kind of thing.
Yeah. This is called recoloring. There's a paper about doing that on graph in a graph-based fashion afterwards, doing recoloring, and they just limit the recursion depth to not make it immediately taking exponential time. But that's definitely that's you directly hit into the NP hardness of the register allocation when you try that. In ACO, we currently are experimenting with some very simple recoloring approach by walking once, after the register allocation, walking once over the program and just checking if the parallel copy can be coalesced with the original definition. Like instead of making one definition and then immediately copying it away, just directly write to the second one.
And can you do that in a kind of tree scanny kind of way, or does it need more traditional liveness analysis and that sort of thing?
You can do some limited amount of it, but the problem is in general so in order to do that, to move the definition and the parallel copy, you need to make sure that everything in between the definition and parallel copy doesn't interfere with it. And in general, I think that requires building up an interference graph, which is exactly the thing we kind of wanted to avoid with the whole scanning approach.
Yeah. So if you don't do it recursively, then you are limited to very few cases where it actually works, that the register was already free. But if you want to do it extensively, you are immediately in the NP-hard graph coloring situation.
Yeah, so all register allocators have some kind of like problem where stuff winds up blowing up and you're like, oh, if only it could have done this. And then this is kind of the area where it happens with SSA-based allocators. You can, I mean, there are so many different ways where you can be like, oh, but if only it did this, then quickly run into NP hardness.
Yeah, we call this the RA lottery in ACO.
I think every driver has
every register allocator has an RA lottery.
I guess your point at the start of your talk yesterday was that on a GPU where spills are really expensive, it's worth doing something that might have extra copies just to get rid of all the spills.
Yeah, that's the theory at least.
Yeah, that's exactly what we do. So ACO does spilling before the register allocation, even before scheduling, so that the spill decisions can be scheduled as well. That's part of the idea. And it it doesn't even call the spilling pass if we know that we have enough registers for the program. And so spilling happens in ACO basically in 1 in 1,000 shaders only. So we really broadly avoid spilling at all if we can avoid it, and only if the program already, like without scheduling, needs too many registers, then we only consider spilling as an option.
We are, however, experimenting with trying to spill some stuff if it can give us a bigger number of waves for the shader.
Yeah.
So if you can reduce your register usage by a couple of registers and that gives you more parallelism, then it might be worth it. I think Daniel had some promising patches for that.
Yeah, we need more benchmarking to see if that actually helps.
Where is that patch, by the way? Because I'd be interested to take a look at that.
Yeah, I can. I think I have that somewhere. I will paste it to you afterwards.
Okay, thank you.
Yeah, is there more questions about it? Otherwise, I think we don't have too much time anymore, so I would like to get into the transition of the...
So with Echo doing spilling ahead of time, is that how IR3 works as well? Does it do spilling ahead of RA?
Yes, it also does spilling, and it is using the exact same paper that Echo is using. We didn't have any time at all to go over the spilling algorithm. I don't know if we can make it and vaporize that out of thin air, but actually the spilling is better because there is a real paper that explains how the spilling happens. So it's a less bad situation than, for example, live range splitting, where there's just nothing. There's just our presentation as far as we know, and a bunch of kind of half-baked ideas in papers.
We do it
ahead of time.
I would really, really like to do it ahead of time for our stuff because when you do it post RA or mid RA, I guess, due to all of our crazy striding stuff, there's a bunch of cases where you have to like unspill and then respill just to get at weirdly strided things. But if we did pre-RA spilling and we were a little bit more judicious about where we picked our spills, we could almost always spill logical values instead of physical values. And that would allow us to take much better advantage of the spill fill instructions that we have available to us.
I think so. The problem with that is that on Intel, like, because you have these like values that are live and then values that are sort of live, the values that are sort of live don't can share the same register, and they can share a register with the actually live values. That means that you don't have that same strict, you don't have that like condition which kind of guarantees that allocation is always going to succeed.
I think we can get there if we have the right interference model. It's just a matter of how absurdly painful it's going to end up being.
I think so.
I think we can get there. I think you need some sort of approximation. The one we were talking about is just like in uniform control flow, you can ignore all this, but then in each, you divvy up each of the regions, the outermost like non-uniform regions, and then you figure out like, okay, how many 16-bit values are there? How many 32-bit values do you need? How many scalar values do you need? And then just add them up.
Yeah, the maximum of each.
And then divvy it, kind of partition it statically between them.
Yeah, I mean, we could still compute a pressure in terms of bytes where we keep track of all of the sort of live, I don't know what you would call them, but the sort of ephemeral stuff that's live in other channels that are disabled as also contributing to that number of bytes or something. I think.
But then the problem is that they can overlap, so you will also overestimate things. And
I think we just have to eat that. Like, there's some amount of overestimating that we're just going to have to suck it up and eat.
Yeah, so either you can overestimate it by like statically partitioning the file and just like assuming that you don't. The case where you would overestimate there is where you have like a lot of 16-bit values live, and then later you have a lot of 32-bit values live, and that kind of overestimates it in that case, but then at least allows you to overlap these ephemeral registers. versus that case is basically the same as your overestimates thing. What you just said basically overestimates things in the same way that your current register allocator overestimates things.
Let me quickly go over the idea of transitioning an existing classic register allocator to this SSA-based approach. So this idea is based on the fact that if you lower SSA, or if you deconstruct SSA, your register pressure does not yet change as long as you insert parallel copies instead of a sequence of copies. So by just translating out of SSA and inserting parallel copies at the control flow edges, if you have no critical edges, at least, I think that doesn't work even if you have critical edges. So yeah, by just inserting the parallel copies at the control flow edges, you don't change your register pressure. So the assumptions that just with getting away with live range splitting instead of spilling still holds.
And if you think about actually when I was coding this up in IR3, I even noticed this, that the handling for live range splits and the handling for phi nodes, the handling for live range, like re-merging live range splits, and the handling for phi nodes is actually surprisingly very similar. Because yeah, you in both cases you have to kind of like insert these copies along the edges, and so you could, in theory, get rid of the phi nodes and just use your live range splitting code.
Yeah, and so the idea would be to deconstruct SSA, but keep the parallel copies in place, and then add live range splitting to your register allocator. Your register allocator can still keep the ability to spill code, but like you can already implement the logic behind live range splitting and fixing up the live range splits. And then you can transition from there by special casing the parallel copies at the end of the blocks, because now it becomes important that you basically handle them as if they are phi nodes in the next block. So instead of already allocating the parallel copy definitions when you finish a block, you can handle the definitions of the parallel copy when you are actually handling the live ins in the next block. But yeah, I think there's a path forward to basically smoothly transition from a classic allocator to such SSA-based, to the SSA-based ideas at least, without interrupting or completely rewriting the register allocator, because that's a ton of work and we will start with a lot of bugs, and then you will have to write a register allocation validator, which you should do if you didn't already anyways.
Yeah, so both Echo and IR3 have this like validation pass, which is a really nice thing because it catches all of your tricky RA bugs, and it gives you if it didn't fail, it gives you the guarantee that your RA is not the source of a bug, some like kind of miscompilation or something. And the way it works is basically just by following each definition from its use and making sure that that register kind of gets there from the definition all the way to the use without getting clobbered. At least in IR3's case, we do it as like a data flow analysis.
Yeah, we also resort to some kind of live variable analysis and check that basically that all the properties hold and the register file is only used by a single variable during its lifetime. Yeah. I think, yeah.
You were talking about converting register allocators, and there's actually a really good paper on this. It's called Quality and Speed in Linear Scan Register Allocation, and I believe it's by some people at Harvard. And it's one of the ones that I dug up when I was working on IBC, and it basically does a SSA-based linear scan register allocator without actually going into SSA, by using a lot of the same concepts and kind of inserting fee nodes and shuffling stuff around as needed across edges. I can provide
does it do swap instructions and stuff, like parallel? Does it insert parallel copies?
It's not the same. I don't remember if they used a parallel copy or not. I think they may have had to in some cases.
Is this the one describing the LVM allocator?
No.
Because I know LVM does do some live range splitting, but then they kind of run into the same sort of problems we were describing, where like they try to like backtrack and stuff, and then it can kind of blow up in your face when you live range split.
Anyway, I'll post a citation to the paper in case anybody's interested. I found it to be an interesting read.
Yeah.
Yeah. Well, I don't have time to scan the paper now, so I'll just keep a tab open. Oh, does anyone want to talk about specifically IR3 and its? We're. I think we have another 30 minutes or so. It starts at 35. It's 2 hours.
Just before that, can I just ask about the transitioning thing? Does anyone know of anyone working on doing that sort of thing to introduce this kind of register allocation on the LLVM target independent code generator?
I don't know of that, honestly. I think someone might have done it for X86, but
SSA-based register allocator.
Yeah, LLVM, like the thing about register allocators is that the design of the register, like the more complex your register allocator becomes, the more the design of the IR becomes tied to the design of the register allocator. And actually, you can remember someone mentioning this on LLVM Dev, that like the design of the IR and the design of the register allocator kind of become intertwined. And it was already a massive effort to rewrite IR3 to use SSA-based register allocation. I had to change a number of things in the IR. So I imagine that if you were to do that with LLVM, it would be basically rewriting everything.
Yeah, that's what I was thinking. It's quite difficult to figure out how you would fit it into its existing framework of, in theory, pluggable register allocators, but they all rely on how MIR works and how live intervals work.
Exactly, yeah. So the data structures kind of become intertwined. It's nice in theory that you can like plug in different register allocators. I don't really think it works in practice.
There's a lot of restrictions on instructions or what you allow in your IR, and then how your register allocator has to deal with that. I mean, all these restrictions on instructions have to be handled by the register allocator.
Yeah, so in LLVM, you kind of just build up this like register file and describe all the constraints very like mechanically. But with live range splitting, you kind of can't do that because the particular constraints impacts the algorithm that you have to use to solve the puzzle, so to speak. And so you kind of can't write your live range splitting algorithm without knowing a bit about the structure of the register file.
Yeah. So, I mean, does that result in a compiler like ACO? That means that if you one day wanted to retarget it to something else, like say Intel GPUs, then you would have to sort of half rewrite all that stuff.
Yeah, I mean, Connor, I think he would have loved to just copy it over, but that
didn't really work out. And yeah, that ties in again to the question I got during the talk of like, and I think Anhalt asked the same question initially when I first mentioned this of like, can we share this? And like, there's shared infrastructure in LLVM, there's a shared register allocator thingy in Mesa, but it just becomes so much harder with SSA-based register allocation.
I suggested to Connor that he should just extend the echo IR with IR3 instructions.
Yeah, so
but that would basically be rewriting LLVM inside Mesa, right? So that's a bit of that.
And run into the same problems of like your live range splitting being heavily dependent on what your registry file looks like.
I can tell that even in Echo, so we have some GPU generations that support a swap instruction, and some older GPU generations that don't do that, and also in SGPRs there's no swap instruction. And this already affects how the register allocator tries to search for available registers in live range splits, because if there is a swap instruction, then it's actually beneficial to reuse the swapped away position of a variable, because then with a single instruction you can just swap two places. But if you don't have a swap instruction, then you want to avoid this case, because then you end up with 3 instructions instead of 2 if you use any other position. So that this is just a very small example how your architecture affects the live range splitting algorithm.
Yeah, and if I hadn't accidentally discovered the swap instruction on Qualcomm, I probably would have done that stuff a little differently too. I would have had to do this whole liveness like scanning thing. So you do kind of have to work on your architecture a bit, I think, if you want to use this sort of algorithm. Like you can't. It brings a lot of benefits for GPUs, and it makes things so much better. But you can't just use it with any architecture. It's not pluggable in that sense.
Is there a swap instruction on Intel actually?
No.
Oh, okay.
Lack of a swap instruction is the least of our problems.
That's kind of true.
Like, when it comes to thinking about things like SSA-based register allocation, our GPU architecture is pathological. And there's a lot of problems that we need to solve before we can get there that fall into the category of academic research. The lack of a swap instruction is, I mean, sure, I'd love a swap instruction, but oh boy.
Yeah. I kind of wonder when the architects add these swap instructions, is it because they're reading these like SSA-based register allocation papers? Like, I can't imagine any other reason why. Like,
swapping data around is a fairly common thing.
Yeah, but even in LLVM, I don't think they have any like optimization. Maybe they have some people somewhere that tries to detect that pattern and turn it into a swap instruction.
I mean, it's hard to represent a swap instruction in SSA. So it's probably not going to be represented in LLVM directly, but like you could peephole to generate it potentially.
Yeah, I guess.
Yeah, I don't know.
This is a parallel copy.
Maybe they just look at CPUs, and CPUs have swap instructions, so like this seems like a good idea. I don't know.
True. If you have SSA with only single definitions, you cannot represent a swap instruction.
Yeah,
well, it gets folded into the parallel copy in the phenode, doesn't it?
Yeah, it's a parallel copy, but that has multiple definitions.
Well, that's one of the other reasons why I don't know how it would even work on Intel, is that the way our hardware is set up is very clearly separated between source and destination, and I'm not even, a swap instruction would have to be a completely different encoding effectively.
And actually, in Qualcomm, the same thing happened, and they did just define a completely different category of instruction where like you have multiple sources and destinations.
I think on AMD it just writes one of the sources.
Yeah.
Yeah. So now that with Tiger Lake we've got the scoreboard-based dependency tracking, swap is probably possible to stick into the hardware. I don't think it would have been possible before without insanity. But yeah, it's, again, swap is the least of our problems.
So what we discussed about Intel earlier today was that the idea to basically statically partition the register file. I think Connor mentioned that already. Yeah, and then handle it as a couple of independent register files, at least within control flow.
Yeah, and then you're gonna have these like live values, and then these like ephemeral live values, whatever you want to call them. And then you probably want to insert fee nodes for them on loops and stuff like that when they're like, the loop is, what's the case where the loop is divergent, and there can be cases where it's like live in the beginning of the loop, but only in inactive lanes because it represents the previous iterations that already ended and have the value waiting for after the loop. But so you want to basically construct that, like if those ephemeral sort of live ranges, and then you probably want to either statically partition or come up with something more clever, and then you want to insert v nodes and copies for those ephemeral edges the same as normal edges, only you use no mask construction when you actually go and like insert the copies and swaps.
Yeah, so statically partitioning potentially works.
The problem with this, the partitioning, is that, again, like similar to what I mentioned with the problem with pre-coloring, like if your static partition is kind of scattered, then you have problems. So maybe what you want to do is like have a way to change the partitioning, kind of, where you just use no mask instructions to move everything around and keep track of that. If you know what I mean?
Yeah, we could sort of we have the no mask instructions, so we can rearrange the partitioning if needed.
And rearrange all of the ephemeral values while you're at it, and then so you're probably gonna need to do something like that, unless you have a static partitioning and it's like not at all mixed, so that it's like one type and then the other type and then the other type.
Yeah, and doing a static partitioning for scalar/uniform values versus vector values would not be too hard. We just figure out what our scalar register pressure is and put all that stuff at the beginning.
Yeah. It's an overestimation, but I think it's not. It's still.
It shouldn't be a terrible overestimation.
Yeah, I mean, what's the alternative? To spill as soon as you don't find a register? That's
I guess the alternative is to just assume that the ephemeral values are actually live, which is kind of what the existing allocator does.
But that's also
an
an overestimation.
add holes to the file. Yeah,
well, but the problem is that that's not the only case we have to worry about, because we have different size values, and we can have, ghost interference. Let's call them ghost values. I like that better, because then they haunt you and they're kind of alive. We've got ghost values that where depending on your stride, you might land on top of them. We can have like 16-bit registers with a 2-byte stride. We can have 16-bit registers with a 4-byte stride, and those can interfere with each other. We can have 32-bit registers interfering with 16-bit registers. We can have, if you have two 32-bit registers where they don't start at the same spot, then you could have the channel masks not line up. Like the number of cases where this can go off the rails is massive.
Yeah, so I'm trying to think of like the data structure you use inside a basic block, because that's kind of simpler than an intra-basic block. That's a whole nother can of worms. But I think the data structure you use inside a basic block is something like for each register, in addition to keeping track of which live values it is, you keep track of which ghost values it has, and you keep track of the stride and quarter of that register, meaning like the ghost values and live values, like which stride do they use, which quarter do they use.
Right. So
and they have to be always, the rule is that they have to always be the same, either scalar or stride of 1 or stride of 2 or whatever.
Yeah, I've written this data structure. I've written a linear scan register allocator.
But that, yeah, so the difference is the linear scan is that thing for each register over the entire, or that thing for each live value. But for this, you want to do that for each register as you scan along.
Yeah, so the data structure that I had basically tracked per byte and had a pointer.
I think that's a bit of overkill. You can probably do it per vec8, I think.
But scalars, we have to deal with scalars, and those can be a single byte.
Yeah, but then you have a scalar type where like this vec8 is full of stuff.
Right. So you can compress it down that way. But
yeah.
At the end of the day, you end up having to track like all of the things that are basically the way I did it was I didn't allow things to overlap if they didn't have matching stride patterns. And
So
that means you can't absolutely calculate pressure.
How many of these stride patterns do you actually have then in total?
So there's one possible pattern for 64-bit values, 2 for 32, 4 for 16.
And how many are allowed to overlap? I mean, how many conflicting patterns do you have?
They all conflict with each other, right?
All?
Well, so basically what it comes down to is that as long, so you don't own, so I should back up. I have more stride patterns than that because you have a stride and anything with the same stride and the same start is fine. So if you insist that everything is aligned to, is aligned the right way, then you can get rid of the multiplicity from the phase. But as long as the phase matches and the stride matches, you're good to go because you can have if you have like a 4-byte strided 16-bit value and a 4-byte strided 32-bit value, those can interfere nicely as long as they start at the same spot. So you can have some things that work nicely together, but the vast majority of your 16-bit values are going to be 2-byte strided, not 4-byte.
I think what you want
I was going to say,
is,
do you really need all those? Like, do we need 4-byte
maybe what you
strided?
do is, so you have a structure that represents, like, what is you divvy the first 64 bits of each vec8 into bytes, and then you say which value is at this byte and what stride is the overall vec8.
Yeah, coming up with the data structure to store the information is tedious, but it's not an especially hard problem. The bigger question is if we get to the end and we have to insert fees to resolve the mess,
I think that shouldn't be a
going to generate and how much of a pain is that going to be? Because
I think that shouldn't be a huge problem. Because as long as you assume that, I think that ghost values that are together kind of stick together, then you either have these like regular fees, which follow the mask, and then you insert parallel copy instructions that follow the mask, or they're like ghost fees, and then you have to insert no mask instructions. You can either move around just the active parts of a value, or move around like all of them.
Yeah. But there's going to be other problems like. So the problem, the potential solution we were talking about to the pathological, what happens if the two ends of my vector are on opposite ends of the register file case, where you split stuff up. I think we will actually have to solve that problem, because you can end up, because everything is strided, you can end up with a case where you have enough bytes for a value, but they're in weird places and they're not in a consistent stride that you can use. And so you end up having to like maybe restride something.
Yeah.
So like if our entire register file is full of 16-bit values with 4-byte strides, and suddenly we need a 32-bit value with an 8-byte stride, which is a thing that could happen, then we have enough bytes, but the only way we can get at it is if we start repacking some of those 16-bit values to have a 2-byte stride.
Yeah, I think that cannot happen if you statically partition the register file, right?
Yeah, if you can get away with a static partition, all the problems go away. It's just a matter of whether or not static partitioning actually works. And we have enough variation in the different strides, especially if you, so if it's a usual GL shader that only deals with 32-bit floats, there are no problems. Everything has a 4-byte stride. We don't.
I think maybe you can assume, maybe don't assume a static stride, but assume that there's still a dynamic partition that at each point in the register file, like it's either assigned to something with a 16-bit stride or a 32-bit stride. And then
yeah, but then you can't do pre-RA spilling without figuring out that partitioning ahead of time, which maybe that's what you do. Maybe you figure out the partition as a first pass.
Yeah, it's what I thought. And the partition can change outside control flow, but it cannot change inside control flow. And then it's only a question of how much do you overestimate your register pressure doing that, and if it's still worth it or not. Because then you might have to spill more than actually necessary, but I cannot imagine that it's really, that the impact is huge, but that's something to test. I mean, you can also calculate this partitioning or the theoretical register pressure with static partitioning and see how far you are away and how much more you spill currently versus you would spill then. That I will and run some shader database and just calculate the difference between the theoretical spilling using a static partition and the current spilling.
Yeah, I'm a little concerned with doing that simply because our current shader databases that we have right now don't have a lot of stuff that uses 64-bit types or 8 and 16-bit types, and I don't want to end up designing something that is pathological in those cases.
You probably just need more Android games then. Just get lots of stuff using medium P.
I think we have a big ton of Vulkan pipelines. I have to ask though.
Yeah, they always did stuff.
I mean, yeah, I think there's some exploration that we can do there, and maybe static partitioning is good enough. In most cases, if all you have is 16 and 32-bit types, then you're only really going to end up with 2 vector partitions. You're going to have the 4-byte stride and the 2-byte stride.
And the uniforms.
And the uniforms, yeah.
How horrible would it be to just pick the sort of physical stride layout of 16-bit values and then just fix that as a pre-pass and then assume that you only have one or the other and you're not converting between them on the fly in RA? Or if you need to convert between them, just insert those before you do RA.
Unfortunately, due to region restrictions, that's a pain in the neck.
Okay.
Because destinations have to be strided out to at least as big as the source stride. And so anytime you like read the bottom 32 bits of the bottom 16 bits of a 32-bit value, the destination of that has to have a stride of 4 bytes. But then there's cases where you can't have a stride of 4 bytes. Like
how does like extracting the low 16 bits of a 32-bit value like in the NUR instruction work then?
We end up generating an instruction that has a strided destination where it's strided out to 4 bytes, but it's a 16-bit type.
And then you just can't pack it, like you just have to use 4-byte stride everywhere. Like,
but there's places we can't use 4-byte stride, so we have to move to and from. Like we have to insert moves to stride stuff out and pack stuff again sometimes.
Okay, so you can do it with a move, but like not with anything else?
Yeah, so moves are allowed to break a lot of rules. So moves are allowed to compact things.
Oh, okay. But then you might be kind of screwed if you need to swap things. I haven't done that.
We can't do it with X.Org.
Yeah, you might need to think that through carefully.
But I think the copies can only happen within the same stride restrictions.
Yeah, so you have to make sure when you insert your parallel copy instruction that all of your strides match. And if you don't have a matching stride somewhere, then you have to insert extra moves either at the source of the parallel copy or at the destination to repack things appropriately.
So, and this is where I was talking about how like it's nice when you have one pass that just like does all of the insanity like in the parallel copy instruction. So if there is a way to do it, like just do some crazy sequence of instructions in the parallel copy implementation, and then you can try to avoid it in the rest of it, but then at least it's that's kind of contained.
I mean, it might be possible, but I think you might be able to back yourself into a corner where you absolutely have to do a swap across strides. And I don't know if that's, I don't think X.Org allows that. I
mean, I don't know.
But if you can detect, like if you can run a sort of simulated parallel copy lowering and detect that that's the case, you can like insert some extra moves to deal with it.
But the thing is that inserting the extra move is the same as resolving a parallel copy. So the problem is that you probably run out of registers, right?
Well, you can reserve. You can always keep one extra register. That's not the case. That's not an issue.
So yeah, we could reserve a register, in which case all is solved because I can do a swap with 3 moves and an extra register.
And yeah, and then you don't, and you can do whatever crazy parallel copy you want, and then just use this extra register to resolve.
The extra register just has to be big enough to store the maximum size swap I'll ever need.
Is that the case, actually? Can you do one?
Actually, can you do like a scalar XOR instruction?
But I might not want to swap the ghost channels.
Oh yeah, that's right.
I would have to think about that. It might be possible with like 4 or 5 XOR instructions and appropriate masking to make that happen.
This is where it gets really like hairy, and at least that's all self-contained. I had to go through a similar sort of thing in IR3 where the 16-bit register in 16-bit mode, you can only access the lower half of the register file. But then sometimes in the parallel copy lowering code, you can generate swap. You have to generate swaps or moves that involve the upper half of the file as a 16-bit register. And then you just have to suck it up and like insert extra instructions in that case. But then at least if everything just works, you can kind of avoid having to deal with it in the rest of register allocation.
Do you know what our worst case was on old hardware to pack multiple bytes in one register if the source is the same byte, like just duplicating the same byte in one register, and now we do some multiply by some crazy magic number to replicate the bytes in the register. But that's all contained in the lowering of parallel copies stuff. So
I think we could improve that by using byte permute, by the way.
yeah, on GFX6, I don't think there's...
Well, not 6, of course, but 8 and above.
I think it's, what he meant is it's only on 6 where you do that.
Yeah, it's
crazy stuff. So there winds up being all sorts of hardware insanity that the parallel copy lowering generally has to deal with. And that's just kind of the way it is. There's the library splitting, which depends on your register file, and then there's the parallel copy lowering, which also heavily depends on what instructions you have. And in the end, like those two parts kind of suck, but then the rest of it is very simple. And at least the hardware insanity is contained in those two parts.
Yeah. Is there more questions about general SSA-based register allocation stuff? Because
any questions about we never managed to cover the register sharing thing that I do in IR3. Variables and the values in the same register.
Stacking the same value in the same register slot, if you know that's the same value, basically.
Which is this whole other thing, which is kind of forced upon me by IR3 not having like the wrong split instruction. No, I don't think so. I think we're getting towards the end.
Yeah.
Can I ask a question that's unrelated to that? So this is an ACO specific question. That you know when you have whole wave mode and on the RRBM backend we have to dedicate a small number of registers to whole wave mode use. So they're VGPRs, but they're used in whole wave mode for reductions and stuff. And Connor, I think you might have done that fix originally. I can't remember.
Yeah.
Is there a better way of handling that with this kind of register allocation?
So you would have a lot of fun with Jason because this is exactly the same problem. But the way it works in ACO is just you have this linear GPR. It's basically reserving a register, but a little smarter.
Yeah, because so there's two things. We have the linear control flow graph and the logical control flow graph, if you remember from earlier. And we just pretend that there's a VGPR, which normally are only live in the logical control flow graph. And we say that this one, then we call it the linear VGPR, is live in the linear control flow graph. And what we additionally do is that we take care that the live range, so that when this variable is created and when it's not needed anymore, that this only goes from outside control flow to, again, outside control flow. And this way we can dynamically allocate a VGPR and dynamically give it away again, while LLVM has to basically reserve it from
the whole program.
Yeah, for the whole program.
So we are reserving it, but inside each non-uniform region separately.
Okay, yeah. Thank you.
So I don't think you can get much better than that without dealing with all of the insanity that Jason was just talking about.
The cool thing, though, is that we can also reuse the same concept for spilling SGPRs to VGPRs. So we do the same trick, basically, if we want to spill some SGPRs, and we can spill them to a VGPR by also allocating a single vGPR for that region and use it there, and then we free it up again afterwards. So
yeah, I think LLVM again does that for the whole function.
Yeah. I mean, it's better than the state it was before that was just broken.
Yes.
So. Yeah, and I think the overhead of allocating it for the whole program is pretty small, because normally you are tied in registers in this region where you allocate it anyway, and you don't really need that register afterwards. So freeing it up doesn't give you much of a benefit anyways. So I think the difference is really small in this case. And you could also see that when LVM fixed that up, that, for example, the performance in the Doom 2016 game increased by like 20%. So and got close to what we achieved. So there isn't really much of a difference anymore by allocating it for the whole program.
Yeah, thank you.
Yeah, if there are no more questions, then I'd also just say thank you for showing up, everyone.
Oh, and I think there were still people were still a little confused, and when we were reviewing IR3 register allocation. So if anyone has any questions and wants to go through the code, probably now this week is the time. But yeah, you can always create a separate room afterwards. I know this is a really complicated topic, certainly not simple to write.
You can also just ping us afterwards if you realize you had another question, or if just something came to mind, or if you were just shy to ask.
So I kind of went through a little bit of it the other day in sorting out that RA validate bug. Which it kind of helps just to like have something to debug and force yourself to go through it.
Yeah, definitely. All right, I think that's it.
Yeah.
Sorry, can I ask something else? Tim, is there a way to reach you on IRC?
Me? No, sorry. I could give you my email if you want. I'm on IRC at the moment, but I'm not generally on there.
Oh, okay. What's your nickname? I will just ping you there, and you can give me your email.
I'm on as NPHCT.
Oh, okay.
So the initials of nice piping hot cup of tea.
Sorry, NPHCT. Okay, got it. Thank you. Sorry.
Okay, then I think that's all for today's workshops. Connor, Daniel, and everyone who was here today, thanks for coming, and see you tomorrow.
Okay, thanks for having us.
Thank you.
Goodbye.
Bye.
Have a nice day.